everybody hear me okay? No? Okay, we'll talk a little louder. How's that, better? Okay, much better. Well, I want to welcome everybody to our February, I'm sorry, not February, welcome to the November Oregon AMS I said I would try and be a little humorous here tonight for Chuck and Gordon and George and for everybody. So, we're going to do something here. It'll take 2 seconds. Just a fun thing. I want everybody here just to look to the right and to the left, take 10 seconds, and greet the person sitting on both sides of you. So go ahead, just say good evening. Okay. Enough. Okay. That's all the fun we're going to have here tonight, okay? I would like to take a few moments to welcome, by the way, if I didn't say, I'm Steve Pierce, I'm the current president of the Oregon chapter of the AMS. Thank you everybody for coming tonight. Holy smokes, 500 chairs in here tonight, so if there's room next to you and you want to give up a chair, please let folks that are still coming in grab one. But I would say, based on what I see now, we're at least 450 so. Yeah. Anyone that, raise your hand if you're next to an empty chair. So people coming in, if you see a hand, you can sit there. It's probably 475 people. Okay, I would like to quickly, say hello to a few people here that are part of the Oregon chapter of the AMS. This is our executive council for this current year. My vice president, the right-hand man, Bobby Corser, he's in the back. Thank you for coming tonight, Bobby. Thank you for being here. Mark Nelson is our secretary. Mark is on duty at Channel 12 tonight, so he cannot be here. John Rainier, our treasurer in the back. Everybody say hi to John. And he's also, we call him the enforcer. Counselors, Tyree Wild from the National Weather Service. Tyree, there he is. Great to have you. Thank you very much, Tyree. Charlie Ferris. Charlie's in here. Raise your hand, Charlie. Retired BPA meteorologist. And George Miller, retired National Weather Service meteorologist in charge. George, back there at the back table. Thank you very much for coming tonight. Folks, I'd like to make a couple of quick AMS pitches here. Yearly dues for any of you that are current AMS members. Your dues are now overdue. Only $7 a year. Please see John at the back table and he will take care of your dues. You can also pay ahead of time. So just multiply it by 7 and you can pay additional years ahead if you'd like. We're on Twitter. There's the addresses. I think there it works. We're on Facebook, Oregon AMS. And congratulations first to the winners of the annual First Snowflake in Portland contest that we had back at OMSI in October. And that is Bob Shaw. And he's in the TV market, I believe, over in Bend. So congratulations to Bob. Robert McKay, AMS member, and Kim Gates. The first snowflakes fell at Portland at 3:53 a.m. on the 15th. Okay, this is another quick presidential note I'd like to pass along here. Due to the unfortunate cancellation of this meeting last November at OMSI, the Oregon AMS and our Treasury had to use additional funds for this evening's meeting that were not previously allocated. So if you find that the information presented here tonight is valuable, please consider making a small one-time cash donation to the Oregon AMS General Treasury with our Treasurer, John Rainier, at the back table. We would appreciate that. And we're also looking for new members. So if you want to become a member tonight, $7 a year, John will sign you up. So please take that into consideration. I appreciate that very much. There are our media partners that we partner up with quite a bit. There they all are up there. So thank you to those who are here tonight and those who also advanced this meeting as well. Okay, here's a couple of additional updates. Here are some great meetings that may just be coming to the Oregon chapter of the AMS. The Executive Council and I are going to work on these hard here in the coming weeks. Dr. Cliff Mass from the University of Washington may be paying us a visit this spring to talk Pacific Northwest weather. Dr. Nate Mantua, he is the author of the Pacific Decadal Oscillation Index. We're going to try and get him down here as well, and that may be a double header, so we'll see if we can get him down at the same time. And Oregon State Climatologist, current State Climatologist, Dr. Phil Moat, and or his associate, Kathy Dello, if I'm pronouncing it correctly. They're going to come up. One or both of them will be up here to talk to us about what is new with the Oregon Climate Services. And then finally, Bruce Sussman at Coin TV will host a meeting there as well, and we'll do a winter recap. So those are all coming up between February and June. So some exciting stuff coming up for those of you who are members or want to become members. All right, folks, now here's the tough part. Tonight's meeting guidelines. I say this with a little pun intended, but at the same time, everybody knows this is a hotbed topic, so please, do note these. Please, no government conspiracy theories, no OMSI conspiracy theories. We've drugged that one through already. Stick to the science of the topic, and just so everybody understands and knows this, that I sent an email out to the 3 presenters tonight asking them to please stick to the science of this topic. And I asked that all of you in here tonight, please stick to the science of the topic as well. If you want to challenge these folks in the Q&A session afterwards on specific things you see here tonight, by all means, please do. We're asking that you keep it professional. No personal verbal attacks, heckling, insults, political attacks. Please be respectful to all. And we're going to just self-police this meeting. I don't foresee any major brawls coming on, so I'm sure we'll do just fine. I do need to disclaim something here. The purpose of the Oregon AMS and our mission statement is as follows. The purpose of society shall be to advance professional ideals in the science of meteorology and to promote the development, exchange, and application of meteorological knowledge. Please note, the Oregon AMS does not, and I want to make this clear, we do not endorse any of the speakers here tonight or the claims or assertions they may make. The Oregon AMS chapter and its executive council have no formal opinion or position on the subject of global warming, aka climate change. Our membership is welcome and entitled to their own opinion on this subject. Okay, so here's how things are going to run. Guest speakers are going to have the podium here any moment from 7:15 to about 8:30 p.m.-ish. And then depending on the amount of Q&A we have, we'll get started right around 8:30 p.m.-ish. And we'll try and close this thing down at 9 o'clock. When we get to the Q&A session, there will be a wireless microphone that I think Bobby has right now, but it will be on this podium right here. Thank you. Just right here by the front computer. And basically, if you have a question, once we get to it, we'll have all 3 members of our panel over here, and we can approach one at a time, or if there's a line, we'll address it. It'll be very simple. 1 question, 1 answer. We ask that it not be debate style, that you don't challenge. Professional challenge is fine, but no verbal attacks or anything like that. What that will basically do is it will get us to just stop the Q&A altogether. So let's try and self-police it. Meeting ends around 9 o'clock, and we'll do our best to get the presentations on the Oregon AMS website as soon as possible, probably in the next day or 2. So I want to do this real quick. If you're comfortable with this, go ahead. If you're not comfortable, you don't have to answer. Just to give you a little background, I got a lot of email from people on both sides of this issue, as you can imagine. The majority of them wanted to have this meeting continue after needing to be rescheduled. But there were a lot of people who were very much against wanting to hear this speech tonight or these speakers tonight. So feel free to raise your hand if you'd like. If you don't, no problem. So out of the audience here tonight, how many of you feel, raise your hand if you're comfortable, feeling that you don't think, at this point in time, your majority of your thinking is humans are not the main cause behind global warming? Go ahead, let's see. Okay. Okay. Now, how many of you here feel that the scientists and the scientific community have the upper hand and global warming probably is human caused? Go ahead and raise your hand now. Okay. So let the record reflect, and this is why I did this, let the record reflect about a 90+%, 10% split. Sounds about right. Okay. So, having said that, Gordon, I think we're going to move on now, so that takes care of everything I've got. So, Gordon we've got to do kind of a quick swap here. Gordon's.
And folks, real quick, if you have an open seat next to you, please raise your hand real quick. We still have people in the back that are looking for seats. So folks in the back, there are chairs available up here. Just try and find a person that has their hand raised. We'll try and get everybody seated so you guys don't have to stand in the back. All right, thank you, folks. Most people will stay. Perfect.
I'll wait just a moment to, thank you, Bobby, by the way. I'll wait just a moment till Chuck's ready, and then I'll go ahead and read his introduction. I'm sorry, Gordon Fulks. By the way, just so you know, we're going to do Gordon first tonight, and then we'll go to Chuck Wiese, and then we'll close the evening with George Taylor. Okay, our first speaker this evening is astrophysicist Dr. Gordon Fulks. Dr. Fulks holds a bachelor's, master's, and PhD all in physics from the University of Chicago. Over the last 40 years, he has worked both in academia and in think tank world environments, studying a wide range of subjects from cosmic radiation to nuclear weapons effects. Pretty interesting stuff. He's even worked one summer for Professor Ted Fujita, aka Mr. Tornado, and on mesoscale meteorology. His work with global warming is entirely pro bono, including numerous op-eds for the Oregonian. He's an avid mountaineer who twice climbed to the 500 millibar level, that's about 18,000 feet above sea level, in Mexico and Africa, and has climbed the last 1,500 feet on Mount St. Helens that no one will ever climb again. Interesting. Dr. Fulks is the son of Joe Fulks, who is a fellow AMS member and member of this very chapter. Actually, let me back up there. Joe Fulks, who is a fellow in the AMS and member of this very chapter, I believe he also worked for the National Weather Service, correct?
Yes,
Excellent, he was out of Chicago. All right. Gentlemen, ladies and gentlemen, please welcome Dr. Gordon Fulks.
What about the control? So,
Yeah, I guess I did.
get used to this. Hang on here. Thanks, Steve, for inviting us. The title of my talk, which is not the approved title, actually comes from an Oregonian headline writer. It was the title of my first op-ed in the Oregonian. That was really the only op-ed which gave me the sort of title that I like. What was originally envisioned here as a low-key scientific meeting to discuss an important topic of wide interest has now become an event that will be watched around the world. The establishment and the promotion of global warming decreed in November that this meeting would not occur because we three senior scientists did not meet their standards. That was a compliment. Thank you very much. Cancellation of meetings has become a standard tactic of warmers who not only find themselves pressed to explain a cooling climate when their computer codes repeatedly predict a warming one, but also completely unable to present any observed climate signature from the gradually increasing carbon dioxide in our atmosphere. Instead of admitting this, warmers promote carbon dioxide as an all-purpose explanation. A Greenpeace activist explained it so succinctly. Global warming can mean colder, it can mean wetter, it can mean drier. That's what we're talking about. You might think that warmers would disavow such nonsense, but they do not. There was even an article in Physics Today recently entitled "Global Warming Could Cause Colder Winters," and it was written by a PhD meteorologist, I'm sorry to say. Science, like climate, is ever changing. That is why scientific meetings like we're having today are important. A few years ago, get used to this. Most people, including virtually all physicians, believed that peptic ulcers were caused by stress. Today, thanks to the work of two dedicated Australian researchers, we know for sure that a bacterium is involved. When Barry Marshall and Robin Warren were awarded the Nobel Prize in Medicine in 2005, the Nobel Committee noted the battle they had waged against the bad behavior of their colleagues who vigorously defended what the presenter called prevailing dogmas. In climate science, we have a similar situation amplified many times, not only by those in authority at institutions like the National Academy of Sciences, but by those ordinary scientists defending their research grants, by university administrators eager to stay on the vast federal gravy train, by politicians who have built their reputations and agendas around an absolute correctness of anthropogenic global warming, by a host of crony capitalists who've been lured into supporting cures for our imagined climate ills by a vast array of subsidies, and by a large number of ordinary citizens who are easily dazzled by those in authority because they lack education in science and because they see this as a new secular religion of environmentalism. Somewhere in the middle is our large and powerful institution, the Oregon Museum of Science and Industry. All it took to send them into a panic were a few phone calls from prominent professors at Oregon universities to remind them that we three musketeers might present heretical thoughts on global warming that might challenge their majority view. What sort of catastrophe are warmers promoting? Are we to be burning in hell by the end of the century as if condemned to the netherworld in Dante's Inferno? Or are they just worried about a milder winter with less valley snow? Are they worried about a return of another Columbus Day storm or another Hurricane Katrina, the melting of the Greenland ice cap and the Arctic sea ice, or just the remaining glaciers on Mount Hood? Or are they worried that you might come to your senses and no longer support their insatiable appetite for research grants? The answer, of course, is all of these and anything else that they think is scary. For them, it's Halloween all year long. This topic has become a catch-all for hysteria, largely because we have let it become so, not because there is really very much to worry about. Now let's turn to the science, where we need to be very clear as to what the scientific topic is tonight. We're addressing the supposition that human emissions of carbon dioxide are warming the Earth's climate in a significant way. This is the so-called global warming. The argument against global warming is so extraordinarily simple and so powerful that we often forget to state it. There is no satisfactory logic and evidence linking human emissions of carbon dioxide to a significant warming of our climate. None. Let me say that again, none. There's plenty of evidence that our climate is changing and that it always has and always will change. Climate simulations that we see a lot of are not proof of anything any more than the wonderful simulations in Star Wars are accurate predictions of what life will be like in the future. They are just exercises in imagination. Real science is more than a good story, more than a tall tale, and more than a Hollywood movie. It requires rigorous logic and evidence. Absent that logic and evidence, theories remain just that, theories. After spending an incredible $100 billion looking for that evidence, it would be prudent to assume that the actual carbon dioxide effect is small and divert our taxpayer money to more pressing priorities. As an example of how good science really works, consider the efforts of Danish physicist Henrik Svensmark to solve the cloud mystery. His hypothesis is that the variable flux of galactic cosmic rays hitting the upper atmosphere causes a variable cloud cover. Extremely energetic cosmic rays cause water vapor to condense in the saturated air. Although each cosmic ray, typically a single proton that has come across the galaxy, leaves only a tiny wake of water droplets, the cumulative effect of many cosmic rays and their shower of secondary particles result in clouds that change the albedo or reflectivity of the Earth and hence its temperature. While this is an interesting and plausible theory, it could have exactly the same problem as the man-made carbon dioxide theory, a minor net effect on our climate. But unlike carbon dioxide, this climate driver has not been studied in significant detail so far. One reason I bring this up is that many years ago, I worked on the explanation for the varying cosmic ray flux of galactic cosmic rays. The theory goes like this. The sun's outer atmosphere is boiled off in a supersonic solar wind that blows past the Earth at 400 kilometers per second. That's 1,000,000 miles an hour. This wind is a superconducting plasma that has frozen within it the magnetic fields that we can measure from the surface of the sun. Because the sun rotates as the solar wind moves radially outward, the magnetic field becomes a giant spiral field. It continues to spread out until its magnetic pressure matches that of the interstellar magnetic field. The laminar flow of the solar wind becomes turbulent, and the solar magnetic field merges with the interstellar field. Incoming galactic cosmic rays are deflected by the spiral magnetic field and become coupled to it. Once coupled, they spiral inward, sometimes hitting irregularities that can alter their forward progression or even reverse it. Of course, as this is going on, the solar wind is convecting the magnetic field and the cosmic rays attached to it out of the solar system. Whether or not they ever reach the inner solar system where we live and the Earth depends on the detailed balance of inward diffusion against outward convection. Because of the complexity of this process, I was careful to step back to a very basic argument linking the sun to the variable flux of galactic cosmic rays in research that was published quite a while ago in the Journal of Geophysical Research. This plot shows the substantial anti-correlation between a galactic cosmic ray measurement, in this case from the Climax Colorado Neutron Monitor, and a solar index smoothed Zurich sunspot numbers. Anti-correlation just means that one goes up when the other goes down. This establishes that they are closely linked, with one likely causing the other. The plot contains one of the very important secrets of the solar system, almost as plain as day. The cosmic ray index lags the solar index by about 2/3 of a year. Realizing that this must be the time that it takes the sun to communicate the solar cycle to the solar system, and knowing the measured speed of the solar wind, I calculated a radius for the heliosphere of about 50 astronomical units, 1 astronomical unit being the distance from the Earth to the sun. That was vastly larger than others believed at the time, and I was advised quite pointedly not to anger those who thought that the heliosphere was small. What I did was what all good scientists do. I acknowledged the arguments of others and presented my differing logic. But what settled the issue? It was certainly not the peer review process that allowed both arguments to be published, but by actual measurements. 20 years later, an American spacecraft, actually several of them, but there was one that did it first, radioed over 8 billion miles home in the longest long-distance call in the history of man, that had finally reached the boundary of the solar system at 80 astronomical units, well beyond even what I said. This is how disputes in real science are settled by real evidence. That's very important to remember. While we're considering astrophysical effects on climate, let's not ignore a huge one. You typically will not see photos of Jupiter in a discussion of climate, but there is little doubt that Jupiter has a profound effect on the Earth's climate. Jupiter is the largest planet in the solar system, weighing in at more than twice as much as all the other planets combined. The Earth would easily fit in the famous red spot you see. In fact, about 7 Earths would fit in the red spot. The red spot is a giant hurricane of sorts that has lasted for at least 4 centuries. The banding of Jupiter's clouds is an indication that different latitudes rotate at different angular speeds, something not possible if the planet were solid. I remember one time I got after the Oregonian for saying that the surface of Jupiter is a very scary place. What's scary is it has no surface. Jupiter is also about twice as warm as it should be for the amount of solar radiation that it gets. This is attributed to its constant slow shrinkage. What does Jupiter have to do with the Earth's climate? There's little doubt that it has a major influence over millennia and perhaps even over centuries. The easiest way to understand the importance of Jupiter is to look at temperature reconstructions from the ice core proxies. This sequence of charts places the global temperature increase over the last 2 centuries in perspective and helps us to understand what the future holds for planet Earth. Needless to say, these charts suggest a future that is far different from what alarmists claim. Incidentally, this is NOAA data. This is government data out of Greenland here. This first chart shows that our world did indeed begin to warm up from the Little Ice Age in about 1830. Extending the chart back to 800 AD shows the medieval warm period. Although ice core data does not cover the 20th century, we show with an arrow where the peak of the modern warm period will likely fall when the ice consolidates in a number of decades. It will be lower than the medieval peak. We know that for a number of reasons. Going back still further, we see a succession of warm periods spaced at roughly 1,200-year intervals, each less warm than the one that preceded it. During the Roman warm period, the great Carthaginian general Hannibal was able to march war elephants across the Alps to attack the Romans. Such a feat is not possible in our latest warm period because of the year-round snow in the mountain passes. Going back 11,000 years through the entire history of this interglacial period known as the Holocene climate optimum, the present climate change is utterly negligible. Note that human civilization developed during this warm period. We tend to like warm periods rather than cold periods. Going back 13,000 years, we see a much different era. What is that much colder period? It's an ice age, which lasted about 90,000 years. Note that ice ages have much more dramatic temperature swings than the benign interglacials. Our recent temperature swing is utterly negligible in this context. Note also that the temperature during the Holocene trended downward as we progress through the Milankovitch cycle that causes the Earth's closest approach to the Sun to move from July to where it is now in January. For the entire ice core record, you have to go to Vostok, Antarctica, where it goes back 450,000 years. The very regular pattern of ice ages lasting about 90,000 years, followed by an interglacial lasting about 10,000 years, were explained by the Serbian physicist Milutin Milankovitch. Question: what causes the small variations in the Earth's orbit about the Sun? That's right, the huge planet Jupiter. And tidal forces caused by the Sun and the Moon change the Earth's orbit just enough to bring about dramatic climate variations. Before I hear objections from OMSI supporters, let me point out that my fellow astrophysicist James Hansen and I agree about Milankovitch cycles, as do most other scientists. That does not assure that this explanation will never be challenged, but it does indicate that it has broad support across the spectrum of global warming opinion. Why is this? Milankovitch was able to prove his assertions with rigorous calculations of the various gravitational effects involved. Because global warming touches on so many topics, can we narrow them down? From the standpoint of climate alarmists, the critical issue is none other than a catastrophe of great proportions, ultimately involving the survival of man and of the planet. This is complete nonsense. What we find in contrast is a profound ignorance of science, even how science works. In one study, half the graduates of Harvard University could not correctly say why the seasons change. This is not a matter of memorization, but a matter of basic curiosity about a fundamental scientific process important to everyone. Should be of interest to everyone, too. For the Oregonian editorial board that I deal with occasionally, and physicist Richard Mueller, the central issue was the warming over the 20th century. But that's a bogus issue also, because most scientists agree that this warming of about 0.8 of 1 degree is about 0.8 of 1 degree centigrade. Similarly, there is no dispute that carbon dioxide is a greenhouse gas, which is much less important than the main greenhouse and climate gas, water vapor. It may also surprise you to know that there is a little dispute as to the warming possible from a doubling of the concentration of carbon dioxide in the atmosphere. The dispute arises when we consider consequences or feedbacks of this warming. Alarmists point to a strong positive water vapor feedback, while skeptics maintain that our climate system is inherently stable against such perturbations because of negative feedbacks. Chuck Weiss will address this in a good deal more detail than I am here. Most scientists who are aware of the global temperature data agree that we saw an increase after the Great Pacific Climate Shift of 1977. As Steve was mentioning, that you'll have Mantua here to talk about the PDL. But that, since 1977, was moderated by several huge volcanic eruptions until they ceased in the late 1990s. Thereafter, the global temperature has fluctuated with essentially no trend. When climate alarmists cannot talk about the logic and the data, they often try to question our scientific credentials or imply that we're in the employ of the oil companies. These are bogus issues. My thesis tonight is simple. Virtually all of what climate alarmists put forth as science is not. Some is half correct, some is incorrect, and too much is just plain nonsense or worse. One of the central problems with anthropogenic global warming is the integrity of the data. This was certainly brought to our attention by the East Anglia emails of ClimateGate fame, but goes well beyond the very bad behavior discovered there. Here is one of the latest examples purporting to show a steady rise in the global temperature since 1973. Climate alarmists have been stunned by the leveling off of the temperature trend over the last 13 years because it goes so strongly against their climate models. Although what you see here is touted as representative of the global temperature, it is merely a compilation and correction of surface temperature data of dubious quality. Note their misuse of the labels skeptic and realist. Here, in contrast, is the gold standard for global temperature measurements. These come from the microwave sounding units on NASA satellites and show amazing detail that is easily correlated with significant climate events like El Niños, La Niñas, and volcanic eruptions. In contrast to the surface data used by warmers that covers mostly land areas, the NASA satellite data covers a large portion of the entire globe. It is amazing that the global temperature is only about a 10th degree centigrade above the 30-year average as of the end of last year, and has been falling because of La Nina conditions in the eastern Pacific. The preliminary data I've seen this month suggests another precipitous drop to below the 30-year average. In any case, we're right in there, very close to average. Why do most warmers insist on using inferior measurements to compile the global temperature? Here is one reason. Urban areas are known to be warmer than the surrounding countryside because of all the concrete and steel and because of limited vegetation. This study shows that the temperature has indeed been rising sharply in the most heavily populated or heavily urbanized counties in California, but hardly at all in rural counties. Hence, any inclusion of temperature data from areas that have seen rapid development will be biased toward warmer temperatures. Such temperature rises are a measurement of development, not global warming. Even the U.S. Historical Climatological Network has enormous biases toward higher temperatures because some sensors have been located too close to heat-producing or trapping structures. Those are pictures from Anthony Watts that show some of the problems, terrible problems. These known problems have become a reason for processing raw temperature data to supposedly address the problems. But unfortunately, it's been another exercise to turn cooling into warming, as the records for this California station indicate. The most famous example of what I consider outright cheating was Michael Mann's famous hockey stick graph. The central theme of all warmers is that everything started to come apart in the 20th century due to man's burning of fossil fuels. The central piece of evidence presented is Michael Mann's hockey stick graph. This graph has had an amazing existence, rising from the ashes each time someone points out a fatal flaw. Why? Because the UN IPCC desperately needs this graph and feels that it can withstand all criticism. The Wegman report to the National Academy of Sciences did not accuse Mann of fraud, but pointed out that his results were not supportable because of serious analytical errors. The East Anglia emails revealed that Michael Mann had used what was termed Michael's nature trick of removing tree ring data that did not support continued warming in the mid-20th century and substituting conventional thermometer records that did. The mismatched data should have told Mann that his data were not reliable, but instead they provided him exactly the result he wanted and worldwide acclaim. That has become an all too consistent pattern with those proving global warming. Here is the corrected version of the infamous hockey stick that eliminates Mike's nature trick and correctly shows the medieval warm period. Mann was intent on hiding the medieval warm period to bolster his claim that we are warmer today than at any time in the past 1,000 years. That is simply not true. Another example of bad science, or other examples are closer to home. Professor Phil Mote, now at Oregon State University, but then at the University of Washington, shows his signature contribution to the global warming debate, an alleged shrinking of the low elevation northwest snowpack. Indeed, the data support his contention from the high reached in the early 1950s to the low in the 1990s. But what about before 1950 and after 1977? Well, he did not think it was relevant to report the entire data set that shows cyclical behavior, but no real trend. You will never see this table of the worldwide record high temperatures from alarmists because it shows that all records for the continents were set long ago. That may seem inconsistent with the fact that we are slightly warmer today than we were in the early 20th century, but it may have to do with less effective mixing of cold Arctic air with warm tropical air when the sun is less active. The sun was generally less active in the early 20th century and also recently. Some temperature records say that we need to be careful about generalities that may not apply to every location. The temperature data for Paris shows the city was warmer in the 1750s and 1830s than today. But also note that the temperature dip around the time of the French Revolution, when Frenchmen were starving due to the refusal of the ruling class to adapt to climate change by switching from growing wheat to growing potatoes. This brings me to my one bit of political advice for the evening: politicians should not lose their heads over climate change. I got a Republican politician really angry with that comment. Because our oceans contain the vast majority of mobile heat on the planet, much of the climate drama plays out there. Climate models consistently predict a steadily rising ocean heat content, but data from the extensive Argo array of deep sea diving buoys tells a much different story. Al Gore loves to tout rising sea levels as one of the dire consequences of global warming. This satellite data would seem to confirm his thoughts, at least as to a modest rise since 2006. But what is wrong? The Swedish scientist Nils Axel Morner points out the scam here. Satellite altimetry shows no sea level rise until unexplained personal calibrations are applied to the data in line with climate models. Basically, they just tilted the record up to match their models. What Morner does is draw the line here you see in blue. This is the sea level trend based on simple tide gauges, none of the complex stuff, none of the modern satellites, just simple tide gauges that show no appreciable changes in half a century in blue. Note how different this is from the steady rise claimed by alarmists. Now, this doesn't take into account rising or subsiding coastlines, which are frequent in many areas, but that's not rising sea level, that's changing in the coastline. Carbon dioxide appears to be another swindle. Here are the famous infrared measurements of carbon dioxide from Hawaii. So far, so good. Here is the way the UN IPCC marries the ice core-derived atmospheric carbon dioxide levels to the modern instrument record. What they do not tell you is that they've arbitrarily moved the ice core proxy records to the right by 80 years and another arbitrary adjustment to make the plot you see pleasantly continuous. What is the scientific justification for that? Essentially none. While the ice cores provide an excellent temperature proxy, they are also a far more problematical proxy for ancient atmospheres. The assumption that they trap a pristine sample of the ancient atmosphere is likely not true, especially for a gas like carbon dioxide that dissolves in water. The other assumption that the ice cores continue to trap the ancient gases as they are removed in a rather brutal fashion from the glacier in the drilling process is also questioned. What is notably missing from the UN IPCC plot of the atmospheric carbon dioxide over the last 200 years? Well, what is missing? All of the measurements made by chemical techniques, basically for over 200 years. Here is a compilation of those from the late German scientist Ernst Georg Beck. Note that his compilation meshes well with the modern IR measurements, but shows much more structure to the measurements prior to 1960. The peak near 1940 follows the warmer period we call in the United States the Dust Bowl. This peak was higher than the levels that alarmists complain about today. Note that Beck lists the researchers involved and references 100 mehr, hundreds more. Several were Nobel laureates in chemistry. If the chemical measurements are correct, and we have little reason to doubt them, they indicate that the dynamics of atmospheric carbon dioxide are much more complex than most believe today, and that levels were notably higher in the recent past. How is this possible, given our greater burning of fossil fuels today than in the 1940s? The oceans also contain the vast majority of mobile carbon dioxide on this planet. Human emissions, while not completely insignificant, are small compared with the amounts naturally in play. Global sea ice, frequently claimed to be disappearing by alarmists, continues to follow a regular seasonal pattern, just as it has for the past 30 years of detailed satellite observations. This comes from a very interesting site, if you don't know about it, Cryosphere Today, which is available on the web and is maintained by the University of Illinois. At the present, this shows that the total sea ice is a little below average for this time of year in the Arctic and a little above normal in the Antarctic. The Arctic low reached in 2007 appeared to be due to slightly warmer water drawn into the Arctic Ocean from the North Atlantic by a reversal in the circulation of the Arctic Ocean. And it's got right down, let's see, back one here. This is the net there of the Northern Hemisphere and Southern Hemisphere, very, very close to normal, actually slightly below normal, but very close. The Arctic Ocean is largely frozen today, to no surprise, and we have extensive snow cover in the northern hemisphere. Such an extensive snow cover has been a feature of recent winters. That would have been a better picture, incidentally, if the satellite that we used to use hadn't failed last September. The IPCC's understanding of climate was better years ago. This is not something they will admit today. The long-term prediction of future climate states is not possible. Today they believe that their climate models can do anything. But all of the extremely expensive climate models fail miserably, not only in predicting the response of the global temperature to increases in carbon dioxide, but also where the warming should be observed. If greenhouse gases were responsible for the small warming we have observed, then there should be a hot spot developing in the tropical troposphere. Without that hot spot, something else has to be driving the warming. The reality is clear: there is no hot spot, and therefore no significant greenhouse warming. The computer models fail again. How can the computer models that so many believe are correct fail so miserably? After all, they include a lot of the basic physics that we all agree upon. The problem is that they are simulations of reality and very far different from exact calculations of the basic physics. Exact solutions of the fundamental equations are well beyond our computer capabilities, as Professor of Theoretical Physics Gerhard Gerlich explains here. Gerlich likens the simulations to computer games, another exercise in virtual reality. In practice, programmers develop subroutines that mimic some real behavior, like large-scale fluid dynamics, but substantially fail to accurately simulate many other crucial phenomena like clouds. To make up for all the shortcomings, programmers use simplifications to make the models appear to fit historical climate data. With hundreds of arbitrary parameters available to them, fitting existing data is relatively easy, but it also renders the codes completely unable to predict the future. The process has become hardly more than a child's game of connecting the dots. Where does a child go when he reaches the last dot? The codes have been trained to project the global temperature relentlessly upward, but that is just what their directors want, and certainly not what the actual climate is doing. The well-known physicist Freeman Dyson from the Institute for Advanced Study at Princeton University once recalled a conversation with the great University of Chicago physicist Enrico Fermi. In desperation, I asked Fermi whether he was not impressed by the agreement between our calculated numbers and his measured numbers. He replied, "How many arbitrary parameters did you use for your calculations?" I thought for a moment about our cutoff procedures and said, 4. He said, "I remember my friend Johnny von Neumann used to say, with 4 parameters I can fit an elephant, and with 5 I can make him wiggle his trunk." With that, the conversation was over. Another fundamental mathematical problem that most scientists fail to understand involves the concept of a global temperature. Such an artificial construct has severe limitations because there are an infinite number of temperature distributions possible for each measured global temperature. Some that involve warm tropical air bottled up near the equator are inherently cooling patterns because cooling mechanisms are very nonlinear. These mathematical arguments may seem opaque to those without mathematical training, but they are very powerful arguments that easily take down the pseudoscience of global warming. Changes in solar activity have long been known to be correlated with our climate. Here you see a picture of sunspots on the surface of the sun. These indications of intense magnetic activity have fascinated man for many centuries, and records of them go back further than any other scientific measurements. They were begun by Galileo in 1611. Here's the entire sunspot record with a prediction out to 2080. The Maunder and Dalton minimums in sunspot number correspond to especially cold periods over the centuries shown. Except we didn't go ahead, so here we go. The Maunder and Dalton minimums you can see there. With strong evidence that the sun is now headed for another slumber, we have yet another indication of global cooling in our future. Because our oceans contain most of the mobile heat on this planet, ocean cycles are yet another strong driver of the climate. Here are Russian records for the Arctic above 70 degrees north, with their prediction for the region out to 2080. Very cyclical. What does all of this tell us? The real long-term threat is global cooling. With this Holocene climate optimum winding down toward another ice age, with the sun entering another quiet period, and with the various ocean cycles heading toward their cold phase, we likely face a cooler future with the next decades to centuries, with a plunge into another ice age toward the end of this millennium. What saves us from really precipitous changes is the buffering of the oceans. They contain enough mobile heat to keep us going for a long while. The real question in my mind, and we're coming to the end here in case Steve is wondering about the time, will we be able to overcome the present hysteria and replace it with a rational assessment of where we are headed? To do that, we must reclaim science from those who are using it for political purposes and religious purposes. As Michael Crichton said, the greatest challenge facing mankind is a challenge of distinguishing reality from fantasy, truth from propaganda. Perceiving the truth has always been a challenge to mankind, but in the information age, or as I think of it, the disinformation age, it takes on a special urgency and importance. Professor Richard Lindzen of MIT is more direct. The need to courageously resist hysteria is clear. Finally, I come to my last slide. I will leave the last word to Albert Einstein. Thank you for listening. If you have any easy questions, I'll be happy to answer them after Chuck has told you that's something to say.
Okay, thank you, Dr. Fulks. Dr. Fulks, we're going to need you to drive that computer again. 2 quick announcements. Raise your hand if there's an empty chair next to you still. If anybody wants a chair, go find somebody with a hand up. We're over 500 now, I'm sure. There is glasses of water, drinks over there if anyone needs them. Bathrooms are out the door, to the right, down near the restaurant. I'll be honest with you guys, I would be surprised if we conclude this by 9 o'clock. So this is their one big meeting, and I want them to finish everything they have to say here tonight. So if you want to hear it all, you're probably not going to leave here by 9 o'clock with Q&A. So,
you don't want to do this again?
Whenever Dr. Fulks is ready, we'll move on to Chuck Wiese next, and we'll just kind of relax here for a second. Wiese is a meteorologist and professional pilot. Chuck holds a bachelor's degree in atmospheric science from Oregon State University in 1979 with a minor in mathematics. Chuck has 25 years experience in operational meteorology and weather forecasting for media and private clients. Chuck is also a forensics meteorologist for the legal community and inventor of the Windicator, for which he holds a United States patent. Chuck also holds has held various positions on the Oregon AMS Executive Council and the Oregon chapter of the American Meteorological Society throughout the years. Ladies and gentlemen, please welcome Mr. Chuck Wiese.
Good evening, everyone. Thank you, Wamsi. This turnout is absolutely fantastic, and I'm really glad to speak to this group tonight because there's so much that's happened with our climate over the last couple of decades that is really contradictory to a lot of the theories that drive the anthropogenic global warming signal. I'm going to talk a little bit about that tonight. And I'm going to pick on a few people, not deliberately, but this is a professional criticism I'm going to give just because of some of the statements that get made about what Oregon's climate's likely to do and the contradictions to all of that. I got interested in this about 15 years ago, primarily for that reason. When I finished my undergraduate work at Oregon State University, everything I learned about climate was contrary to what was being put out by people who believe in anthropogenic global warming. In other words, we didn't learn back then that the greenhouse gases could amplify the climate signal like is being advertised with these climate models in their code. So I started asking some questions, and unfortunately I could never get a straight answer. And so this caused me to get more and more interested and start digging more and more, and the more I looked into it, the more I began to realize there were some real problems with the data. So I'm going to take a look at that tonight. And we're going to start out here by some information that was put out by local county governments. But this comes from the Oregon Climate Change Research Institute, where Phil Mote does his work. And they show two graphs, or two depictions here. One on the left where it shows planet Earth from 1880 to 1889, and then the difference in temperature from 2000 to 2009 over a specific mean, and they show, well, it was getting colder back then before the turn of the century, and for the last 10 years, everything supposedly is getting warmer. Well, what's wrong with that picture? It fails to show the cyclical nature of temperature, and actually for the last 10 years, it's questionable. In fact, I doubt whether the global temperatures have really gone up. But yet that's the information that was presented here. And then emerging impacts from increasing CO2. I just have a problem with this because I want to know where they're getting this from, and I can never get an answer other than, well, our climate codes are telling us that we can expect drier, hotter summers. And I'm thinking to myself, a drier, hotter summer because of increasing greenhouse gases, that's not how they work. They don't cause temperature extremes, they actually constrain the temperature change. We'll talk about that in just a second. Then they get into sea level rise. Gordon's already covered that. I think George Taylor's going to talk about something too. But basically, the predictions are very dire consequences for us. And Mr. Mode has used climate modeling to say that temperatures of Oregon could rise by as much as 9 degrees on one extreme. Anywhere from 3 to 9 is his best guess by the year 2080. And again, I have problems with this because that's not what the real data is showing. In fact, there's little or no support for it, and I'm going to show you why I believe that. There has been some warming in the last 100 years. Climate at a glance from the NCDC temperature record shows that back before the turn of the century to now, there was a little over a degree of temperature change to the warmer. But notice the temperature is cyclic in there. There was some warming and cooling periods, and but the overall trend from 1895 to now was just a bit warmer. But that's not what the climate is doing right now. This was the best temperature record. We just learned about this recently. Remember reading about that in the paper? This was the Berkeley Earth's surface temperature data, completely reconstructed, and of course they were saying that the record was indisputably showing that the temperatures are warming at an alarming rate. And I'm choosing a period of time tonight to show these temperature swings because I'm also going to compare the CO2 increase since that time. I'm using Chicago's Modtran radiation code to show the effective change in the outgoing long-way radiation for that increase in CO2, but we're going to add a second feature into that tonight. We're going to show how the water vapor changed. Because the one thing that hinges upon the global warming theory that they have to have in order to get their temperature rise is they have to grow the water vapor optical column as they increase CO2. If that doesn't happen, they can't possibly get the warming that they have been predicting. On the bottom of this graph is the satellite global temperature records for land only. That's important to distinguish. This is land only. It's not the oceans. The oceans do not show these trends. If you were going to take a look at the last 10 years of temperatures, you want to know the real trend, there are low cycles that happen within a 10-year period that can be influential to our temperature. We talk about them all the time at our winter weather conferences. There are the El Niños and the La Niñas, or the La Niña this year. If you're going to look back 10 years, why do you choose just 10 years? It may not necessarily be 10, it might be something close to that, but it's important to have an equal number of El Niños and La Niñas so that you can signal out that, or filter out that noise to get a true idea of how the temperatures are going to change. So if we look at an equal number on the Oceanic Nino Index, we've got to go back to 1998 to compare that up to now to get the true temperature trend. And it still shows a slight rise in the Berkeley record, about a quarter of a degree, but the global satellite record shows the trend is pretty much virtually flat. That's not something that was forecast by any of these climate models. Now, I've heard excuses saying, well, they did kind of predict it, but no, they didn't. I'll show you that a little bit later in the presentation. If you include the oceans, which is the Hadley CRET-free data set, and also the global satellite temperatures from the University of Alabama, Huntsville, the global record actually does show that from 2002 until now there has been a downward tick in the temperature, and the green line is where the CO2 has been going up. That's an interesting dichotomy to somebody who's going to claim that CO2 is driving the climate. Why isn't it going up? Their models said that it would, and that's clearly not what the last 10 years of record have shown. And to make things worse, this is the NCDC temperature record for the last decade, actually just slightly longer than that, for the 48 lower continental United States. The trend is down, not even steady. For this land area, it actually went down almost a full degree. Now, if there's going to be any changes because of changes in radiation, which areas would respond to those changes first? We know it has to be the land because it's got a lower heat capacity than the oceans. The oceans absorb an awful lot of heat. They buffer the temperature, like Gordon said, and it takes a long time to see a temperature signal emerge from the ocean, much longer than it does over the land. This, to me, is a very alarming trend for somebody who wants to continue to believe that CO2 could drive our climate. We're going to talk tonight a little bit about electromagnetic radiation. I know that's everybody's favorite subject because it's popular as the Blazers, right? No? Well, maybe we'll have to shorten this a little bit. But we're only going to go over some basics because we've got to get into radiation tonight to talk about some of the changes in the outgoing long-wave radiation. This here just illustrates the whole spectrum of electromagnetic radiation. When we talk about radiation, a lot of people think, well, that's that dangerous stuff that's hazardous to your health. It can be, but it comes in all sizes and amount of energy. And that's what separates the most energetic part of the radiation to the least energetic, is the size of the wave and the quanta, or little packets of energy that run along the wave. At the top, where Gordon was talking about cosmic ray photons, we've got a couple hundred picometers of wavelength. That's extremely small, and a lot of energy riding in the wave. That energy splits apart a lot of things. That large molecules are changed by it. They ionize things. It's very hazardous to your health. It's like taking a machine gun with small bullets that you can't see and firing right through you. You make a mess of your molecular structure of your body because of the energy and the size of the wave. As you go down towards visible light, the size gets bigger, the quantity gets smaller. Now we have a radiation that's friendly to life. In fact, the visible light primarily is what is responsible for heating the Earth, along with some ultraviolet radiation. And then just below that, the infrared stuff. So it's this stuff right here that we're going to focus on tonight. By the time we get down to radio communications, the size of the wave is so big, it can be a couple hundred meters in length. That doesn't interact with atoms anymore. So that's why we can have radio communication, and none of those waves get intercepted by the smaller atoms. If someone was dumb enough to build a transmitter at 15 microns where CO2 absorbs energy, what do you think will happen? You turn on a radio and a couple hundred yards away, you couldn't hear anything but static. But the guy by the temperature, guy by the tower that has a thermometer might measure a temperature rise because all the radiation got absorbed by the atoms. So they get attenuated by the size of the wave and the quanta. So enough about that, you get the basic idea of what we're talking about. This is one of my favorite graphs to describe how these processes work in the Earth's atmosphere. Now that we know that the radiation size of the wave and the energy it has is based upon the wavelength, we can plot two graphs, one of the sun and one of the Earth. And the sun has a temperature on the solar surface of roughly 5,500 degrees Kelvin. It's pretty hot. Its maximum emitting wavelength based upon that energy is a half a micron. Earth, on the other hand, is much colder, has a mean temperature of 59 degrees Fahrenheit, 288 Kelvin. So its wavelength that it has to emit energy at is 20 times longer than the sun's. It's because of what I told you about how things change with that. The solid color means that all of that radiation from the sun is pretty much transmitted, a lot of it, to the Earth's surface. Where you see these little squiggles in here, these things, that's where you're getting some absorption of energy by the sun from some of the constituents in our atmosphere. If you compare that to the Earth is emitting energy, but notice nothing's colored in, only a small area. That means virtually all the radiation leaving the Earth is absorbed by a lot of the constituents in the atmosphere. That's where this global warming theory comes in, because they're arguing we're absorbing more infrared radiation and we're going to cause the temperature, therefore, to go up. Let's take a look at what gets absorbed. What is the number one constituent that gets virtually most of the Earth's outgoing radiation? Well, here it is. Water vapor. Look at the number of absorption curves on that and the various different wavelengths it gets the radiation from. It's huge. It takes up most of the absorption here. It is the main greenhouse gas that regulates the amount of cooling and some of the warming that Earth gets. Below it is carbon dioxide. Look how small that is in comparison to water vapor. In fact, about 37% of carbon dioxide's wavelengths are intermixed with water vapor, further complicating that situation. Carbon dioxide gets about 17% of the total radiation leaving the Earth's surface. Water vapor gets the rest. It's not very large. So, it doesn't have much of a controlling effect at all. Now, people will say, and I've heard the argument that, well, so what? If you add more CO2 and you're getting more of the outgoing long-wave radiation, why wouldn't the temperature go up? Well, there's a good reason for that. We're going to talk about it. You meteorologists will really like this one. When I was in undergrad school, this was a graph that was just beat into our brains. It was the work of a guy by the name of Richard Emden. He was a physicist who wanted to know what happens if I take water vapor, put an average amount that's on the Earth's surface, just lay it down like it is on the real Earth's surface, and decrease it exponentially with height. I'm not going to allow any transfer of energy from the Earth's surface into that layer by conduction or convection. I just want to know what changes from the radiation that gets absorbed by the ground and by the water vapor. What he found was there's so much infrared absorbed by water vapor in this thin layer near the ground. And down here, it's very intense 5 micron absorption, which I just showed you on the last graph. At the top, it emits there where it's colder, but it also emits at the longer wavelengths near 20 microns. You get a huge amount of cooling, not warming, cooling, caused at the top of the layer by the radiation coming off the top of that layer, and you get a lot of absorption at the ground. So you create a temperature gradient in the vertical. This is height and this is temperature, increasing to the right. So you get a huge, huge temperature decrease with height, so much so that the density of the air actually increased with height. Any meteorologist will tell you that is an impermissible state based upon the hydrostatics of the atmosphere. You cannot have that condition without overturning it and getting the hydrostatic balance back. So that's exactly what happened in the Emden model. It overturned, and in a big sort of way. You ride a dry adiabat up to condensation, because when that air starts to rise, it's going to cool. Now the water vapor is going to condense, and what does it do? It releases latent heat back to the troposphere, so it rides a moist adiabat, and it's able to stay warmer than the environmental temperature all the way to 8 kilometers above the surface. That's huge. And then there's so much vertical velocity to that particle going up, the moist adiabat, it overshoots it by 2 kilometers and finally stabilizes at 10. That is the tropopause, formed by water vapor alone. CO2 had nothing to do with it. Now, when Emden looked at this work, he found one problem with it. And the problem was that he had the wrong tropopause temperature orientation from the equator to the pole. His result showed that the tropopause temperature at the equator was warmer than the pole. That's not what we observed. We observed it's colder at the tropics, warmer at the pole. Well, then another physicist came along and looked at the problem. His name is Richard Goody. Goody was Dick Lindzen's academic advisor at MIT for his doctorate in meteorology. And there's no question Goody is a brilliant atmospheric physicist, he wrote the book on radiation transfer. He just said, let's throw CO2 into the mix and see what we get. So we did. What happened? As you threw CO2 in, 15 micron emission strongly cooled the upper troposphere, and you got additional enhancement down at the ground by throwing CO2 in the mix of causing some warming, causing further overturning of the atmosphere. It's important to realize before that result was put in, what did you get with the water vapor alone? When you caused this overturning, you created three things that were important to understand before you throw CO2 into the mix. Water vapor self-constrained its ability to grow, because by creating that moist adiabatic ascent, you created a cloud cover. You start blocking sunlight by putting latent heat back into the air, and you created a hydrological cycle. The hydrological cycle is basically taking all that heat energy from the ground and is precipitating it out back to the Earth's surface, so that you get the right balance by water vapor that it feels comfortable with by the amount of energy it absorbs combined with the solar coming down from the solar energy coming from the sun. So when you add CO2, you're enhancing the hydrological cycle more than you're creating much in the way of any warming from it. I'm going to take a look at the molecule. And this is interesting. We focus now on CO2. And what the graph shows is wave number across the bottom. These physicists like to confuse us because wave number is the reciprocal of wavelength divided by 100. So they take it per centimeter. 667 is the center of the 15 micron band. That's 15 microns, about 667 per centimeter. But you cram 667 quanta in a centimeter of length. Notice how intense, first of all, I need to explain a few other things. Across the top is transmission. And transmission is the amount of energy, if radiation is passing through a medium and it starts to get absorbed, the transmission starts going down. It means what's leaving the layer as I look at each one. I'm adding all this up. So if the transmission's 1, nothing was absorbed. If it drops to 0, it's all absorbed. So we color-coded these things to show how much height or depth in the atmosphere you have to go through to get this absorption. And at 15 microns, the absorption is very rapid, very immediate. The brown color stands for the equivalent of 1.39 meters above the surface of the Earth. It's not very much. Maybe 5 feet, 4 feet. Just that far above the ground, this radiation is absorbed immediately. By the time you get to 139 meters, the blue colors go from the top to the bottom, meaning all that energy at these wave numbers is absorbed. And by the time you get to 1,000 meters, which is the red color, that's pretty much the whole 15 micron band. It's completely absorbed. And what it means when you absorb it that low is, that's to the ground. That's what we mean by saturation. You are absorbing it so rapidly near the ground, the transmission back to the surface is about the same temperature in the air as it is to the ground, so you're getting a maximum bang for the buck when you get it absorbed real fast. If it takes longer, then you have to start calculating your emission at a higher height in the troposphere, and it's colder up there, so you can't get as much energy as it takes more and more space to absorb. 200 parts per million by volume of CO2 and even less cause that 15 micron band to saturate like this. We had nothing to do with this. The natural amount of CO2 in the atmosphere absorbed all of that energy, and in order to get more out of it, we go to these green colors, but before we do that, we have to go up to 6,800 meters above the ground. Now you're really getting up there, close to 20,000 feet. Now if you double CO2, here's what you get. But notice the amount of path you have to go through to get that result. Instead of absorbing this right near the ground, now to double it, this is what they call the wing line stuff, way out at the edges, you got to go up to around 20,000 feet. An interesting question for a climate modeler: how do you sort this out with the clouds? if you're getting various different amounts of absorption all the way up to 20,000 feet, you've got a problem. And also, because even at the main bands, you're enhancing the hydrological cycle by increasing the CO2. You're not really increasing the temperature much. Out near the edge, it gets worse because you have to go up so high to get any increased absorbing effect, and that 15 micron band is still emitting at its own temperature higher up in the troposphere. The net result is, it's kind of a change in components. We did get some enhancement here, but as you go out here, it's harder to get. Because now you're doing what? Cooling the troposphere. The fact that these gases do that is indisputable, and it's strong evidence that you cannot change the water vapor optical depth like the climate models say you can, and that's critical to their forecasting a warming temperature. Well, here's some calculations that were done by Modtran. This I didn't do. This is a computer program from the University of Chicago to illustrate what I'm talking about. I plotted these up myself or took them straight off Modtran. They've got a neat program where you can go online and you can pick any altitude you want and get their theoretical radiometer at any altitude and get the absorption in an emission in both directions. And so I did this for CO2 going from 0 to 375 parts per million by volume. And here's the absorption. Starts out from 0, 2, 4, 6, 8, 10, 12 kilometers. 12 is very near where the tropopause is. So by the time we get up there, we've absorbed a little over 27 watts of energy. If we count the downward emission, which is actually just the emission at the local temperature, the upward flux is what's attenuated by the ground. The downward flux is just the emission at the local temperature. Well, it's kind of hard to look at this without studying a while to see what you're getting from this. I computed the changes through each layer, whether you're getting energy, getting more energy, or losing energy. And lo and behold, if we want to color code this, we get the better example of what we've actually done by going from 0 to that amount. There it is, above 4 kilometers, the effect of adding CO2 from nothing up to where we're at now, or pretty close, cools the upper troposphere. So you're going to trim water vapor out, which means you're going to enhance the hydrological cycle, but you can't grow that column. That's critical to the climate models. And as proof of that, you can look at just taking a box of carbon dioxide. And if you take the box and just let it sit, don't add any energy to it, the red line here is the emissivity, or the amount of energy the gas emits, and over time it just goes down without actually cooling it by conduction, just letting radiation do this. And the temperature then starts to go down as well. It's a total change of almost 3 degrees. And it just keeps trying to do that until something wants to warm it up again. So that's how the effect of these greenhouse gases work. So if we want to take a look at carbon dioxide from 1960, which is where that best temperature record was that I showed you, let's take a look at CO2 from 1960, where it was at 314 parts per million, and at 2011 up to 389. That's the measurement from Mauna Loa. What are the changes in the radiation using the Modtran model at the University of Chicago? Well, from that amount in 1960 till now, the outgoing long-wave radiation decreased by 1.1 watts per square meter by going from 312 to 389. The downward was like plus 0.557. Well, the NCAR people and the modelers want to continue to insist that their climate modeling is correct. So they couple that result that I just showed you, and they claim that the water vapor has been going up consistent with modeling. That's always what they say, consistent with the modeling. 1989 till now shows that the water vapor column amount has gone up by 1.2% per decade. But why would you just show the record from 89 till now when you have a more thorough record? Just like, well, they murdered us is what they did. They they don't show the complete record. And there's no reason not to, because if we take a look at the complete record, we get something completely different. Here's the temperature going up, as I showed you with the best temperature record and global satellite stuff. The CO2 is certainly going up. It's measured here in atmosphere centimeters, which is this like scale height in CO2. If you had an Earth atmosphere of it, it would be about 5,000 meters thick. So if you divide that into 5,000, you get the atmosphere equivalent in CO2. And the H2O column amount, that's measured in precipitable centimeters, so it's like, how much could you collect in a little 1 by 1 centimeter collecting dish if you basically condense it all out of the troposphere? And the answer is, the mean is 2.6177 per square centimeter. Notice on this graph, from where NCAR took the data, there is a slight upward trend. You can probably draw a positive trend line close to what they did. But if you go back to it's a 61-year record, 1948 to 2008, just 2 years ago, the amount of water vapor in the troposphere has actually gone down. That's a huge inconsistency with what the modeling tells us. What does it all mean? Well, in order to have the HEW theory verify, it requires an increasing global average optical depth with increasing greenhouse gases. If you add the tau values, which is basically the optical depth, the changes in them for all three of these components, they've actually gone down. Increasing temperature decreases it, decreasing water vapor decreases it, CO2 increases it, but where are we getting the warming from? It isn't there. And I challenge anybody to show me that it is. This graph is from Dr. Ferenc Miskalzi. I'm not going to get into the theory of his paper. It's still being reviewed by a lot of people. But you can't dispute his collection of data that he used to form his hypothesis. And he computed using what we call the Torvalds data. It's called the Tiger data, actually, Torvalds Initial Guess Retrieval. It's from NOAA. And he got a very extensive network of radio sound observations to come up with these changes in water vapor optical depth. And basically plotted them against the optical thickness, and wrote a fourth order polynomial, which is the blue line that pretty much describes the change in optical depth as a result of the change in precipitable centimeters of water vapor. With this, you can use the general form of the Beers-Lambert law, and you can compute the change in radiative flux at the top of the atmosphere. So I did that with this data, and the change of 0.649% as CO2 went up to those values that I just told you about. Here's what I came up with. The projected mean global radiation change from CO2, as I showed you in that earlier graph, was 1.1 watts per square meter from the Montran radiation code, and the Earth albedo reduction, because this is clear sky radiation only, so we have to take 31% out of it, because we don't know what it is for clouds, we can't model them, and every modeler knows that. And then from the Tiger water vapor profiles, Dr. Miskalzi's data and workup showed the optical depth of the water vapor column dropped by 0.649% from that 2.6117 precipitable centimeters over the 60-year record. Well, from the Beers-Lambert formulation, the surface upward flux of radiation from the ground multiplied by the transfer function is equal to the outgoing long-wave radiation, where F is 2 over this quantity here, 1 plus tau plus e to the minus tau, and that equals 0.35 watts per square meter, again reduced by 31% because it's clear sky only, and you get an increase in outgoing long wave of 0.24 watts per square meter. Final tabulation, what is it? There's the 0.76 from the reduced amount of CO2 minus 0.24 from water vapor. That's 0.52 a decrease of 0.52 watts per square meter of outgoing long-wave radiation. Well, if you take the derivative of the Stefan Boltzmann and divide that by the result at the meter temperature of 59 degrees, the total change in temperature, if you could believe all of that, right to the exact calculation, would only be 0.10 degrees centigrade, or 8.3% of the actual temperature rise that occurred from 1960 to 2011, and that's in the most optimum conditions. What does that tell us? It tells us we can't explain in any certain term what that temperature rise was really all about. We have suspicions, but it wasn't caused by carbon dioxide. That's hard to dispute when you got data and you can make a calculation, which I just did. Well, Gordon covered this, but I'm going to go into climate models a little bit because I'm going to show you just how bad some of the results have been. Well, Professor of Mathematical and Theoretical Physics, Gerhard Grülich, said, to derive climate catastrophes from these computer games, which is basically computer model climate code, to scare mankind to death is a crime, and I believe that. I think it is. It's not right. It cannot be overemphasized that even if the fluid equations are simplified considerably, one cannot determine numerical solutions even for small space regions and even for small time intervals. This situation will not change in the next 1,000 years regardless of progress made in computer hardware. As the extremely simplified one fluid equations are unsolvable, the many fluid equations would be more unsolvable. The equations that included average equations describing the turbulence would be yet more unsolvable if unsolvable even had a comparative. In other words, these things expand a lot, and a lot of assumptions have to be made by working with them. Hence, computer simulations of global climatology are not based upon the physical laws. Jim Hansen doesn't like this graph because it shows what he projected from his climate modeling based upon increases in CO2 emissions, and plotted on that is the actual temperature change. He ran 3 models, 2 of them showing drastic increases in the temperature as our emissions went up. This one was based upon drastic cuts to CO2. We haven't made any cuts anywhere. It's going up. But even with the drastic cuts, he projected the temperature would be far over what it is. We're running at about 0.4 degrees above the 79 mean. And right now, 2010, he said we'd be up here at 1.2. Several times larger than what we have actually experienced. No discussion about that. Let's just sweep it under the carpet and say we've improved the models. Here's the same thing for the first, second, and third annual reports to the IPCC. This is a climate model projection used for each one. And this is a committed to the reduction strategies that they seem to want to come up with, and they say this is how we can level the temperature based upon that. And here's the temperatures that I plotted below it from University of Alabama at Huntsville. We're way below where those projections were for any one of those, and going nowhere north fast. It's obvious there's a serious problem with the modeling. This is one from Phil Mote. His projected temperature increases based upon the local climate models he runs for the Pacific Northwest. I assume that's the tri-state area, Washington, Oregon, Idaho. And notice again, he's got an average scenario, the worst case, and best case scenario. And this is the temperature leveling off versus the rapid increases that he projected in those scenarios. Obviously, not happening. Nowhere close. No admission, though, by these guys that they have a problem. They just continue to insist the modeling is good and it's consistent with everything that's going on. This was off of AR4, the most recent IPCC report, that shows the same thing. They brag about how they can accurately project temperatures. They show the temperature in their forecast by these 2 lines. And they cut it off, though, here a little after 2000 because they don't like the fact that they continue to forecast the temperature to go up, and that's not what we're seeing. So let's just chop it off. That seems to be the order of the day. And of course, Gordon explained this one to you, and it goes back to the basic meteorology that I was talking about at the beginning. If you are going to warm the Earth with carbon dioxide or any other greenhouse gas, the way the climate models say that you can warm it, they were forecasting the opposite of what the physics dictate should happen as you add more of a greenhouse gas to the troposphere. Because they enhance convection, which would happen, but they don't take into account the strong radiational cooling that goes on in the atmosphere when you add more of a greenhouse gas to it, when you're throwing latent heat back at it. So they get this unrealistic hotspot over the tropical troposphere, which allows them to raise the surface temperature considerably, because then, once you've done this, you have to get a warmer temperature at the ground in order to convect heat away from it. That's how it works. You tend to create these inversions that way. But it's wrong, because in reality, this is what we have. None of the stuff they forecasted in the tropical troposphere ever materialized. Their physics cannot be correct. So what can we conclude from all of this? Well, there's nothing in the real atmospheric record that supports the recent temperature rise in the last century to carbon dioxide-induced anthropogenic global warming. How can you make the case that there was? The tropospheric water vapor optical depth is remarkably stable, but it has declined. That's extremely important. It declined slightly, not much, but boy, it went down over the last 70 years of record as carbon dioxide rose substantially in the atmosphere during the same period. This is consistent. A consistent outcome is expected by the first principle found in physics and inconsistent with atmospheric climate modeling. Without water vapor acting as a positive feedback to increasing carbon dioxide, which is what they forecast, the projected radiative forcing on the Earth's surface is but a grossly exaggerated calculation of what the Earth's temperature will actually do in response to continuing to increase it. The Earth's greenhouse effect is not controlled by atmospheric carbon dioxide. It is modulated and governed by atmospheric water vapor and clouds, where the warming modulation is controlled by the amount of water vapor and that optical depth that I was talking about. Clouds with a hydrological cycle act to trim out water vapor into a hydrostatic convective equilibrium. The Earth's gravitation and hydrostatics dictate that. The stable atmospheric optical depth likes the mean Earth temperature of 59 degrees without further solar or planetary modulation. Remember, it's only solar that can change the water vapor optical depth, because it doesn't cool the troposphere, it warms it. The greenhouse gases don't do that. The anthropogenic warming hypothesis by atmospheric CO2 is falsified by the real record and the radiation physics if you take a look at the appropriate time periods. So what might have caused the temperature changes? Well, I'm really a strong believer of the solar magnetic. The sun is the main source of energy that heats the Earth, we all know that. And it only makes sense that modulations in that energy could cause big changes in temperature. And this is the work of the Russian physicist Habibullah Abusamatov, I think I pronounced it right, and what his projection of the solar magnetic is going to be for, and Gordon briefly covered this, for the next several decades. And notice, again, he defines a hot sun as anything with a Wolf mean sunspot number above 75, which is a line we draw right here. And a cold sun when we have a solar cycle with anything less than that 75 Wolf spot. And notice, when you approach the problem that way, this matches up very closely, a correlation of R squared like 0.96 of warming and cooling of the Earth's temperature. And the important thing is, based upon the Jovian planetary effects that Gordon was talking about, these guys are forecasting the sun is going to go into a deep hibernation. And so did Theodore Landscheid, who started the work in the United States. He died in 2004. He'd be celebrated today because he had a bullseye as far as getting it right with the way the solar magnetic has changed. What would we expect in temperature if we start getting this cool sun that the Russians think we're going to get, and along with American scientists who study the problem too? According to him, he thinks the new beginning start of a miniature ice age will be just a few years away. When the last solar minimum hit the Earth, we, for the first time, got some measurements off the satellite that showed the amount of ultraviolet radiation coming out of the sun drop a whopping 7% at the top of the atmosphere. It was huge. Ultraviolet radiation heats the atmosphere, and it also heats the surface. Not as much of the surface, because a lot of it's absorbed by the ozone in the upper atmosphere, but nonetheless it's part of the heating mechanism. And he forecasts that the solar magnetic will drop off to the equivalent of a loss of about 2.5 watts per square meter as we get into solar cycles 25 and 26. And then he projects this is going to go on way past 2040. We'll likely see either a moderate or Dalton type minimum. If you lose that much energy off the sun, you got a problem. You really do. And this is something that's very big and something we have to pay a lot of attention to. So the conclusions of my presentation from changes in solar magnetic off the sun are that based upon the near perfect correlation of R-squared values between solar magnetic and temperature, the outlook for the Earth, in my opinion, and not just mine, a lot of the solar physicists as well, for the next 50 years is a considerable amount of global cooling that will likely have significant impacts on growing seasons and energy consumption. We better be thinking, in my opinion, on this way, not for warming. The outlook is based, the outlook is based upon the continued accurate projections given by solar physicists Landscheid, Abdusamatow, Penn, and Livingston. All these guys have done really good work in their projections of what they think is going to happen. Carbon dioxide radiation is insignificant to the larger picture. It does not drive the climate. There's no measurement today that proves that it does. So in terms of Oregon's weather, I thought I would show this interesting graph as I finish my presentation. This is a graphing of snowfall in Portland for the last, well, since 1980 per year. And you see, we haven't had a lot of snow. The old-timers and their historical stories are a much different picture than this. They talked about when the first settlers arrived from Europe and Oregon, they documented huge snowfall amounts on the east bank of the Willamette River. Fortunately, the Weather Service kept all that data and we still have it available. Why would there be any reason not to believe this will, or I should rephrase that. Why would we want to believe, based upon solar magnetic and the changes in it, that these snowfall totals per year would stay just like they are if we're going to lose that much energy off the sun? I don't think it's a reasonable assumption to say that they will. Well, what did they look like before the year 1900? Portland was not such a nice place to live in the winter before the year 1900. Look at some of these snowfall totals. In 1892, 60.9 inches, 50 inches in 1871. A lot of years that we would consider to be extremely harsh. Well, we were just coming out and ramping up to a grand solar maximum if you look at the solar magnetic stuff when we left this particular century. And I think that's largely the reason why we saw these snowfall totals decline, because we did get some warming, and I think the sun was the primary driver. So my forecast for Oregon is more of this. Sorry if you don't like it, but I think that's what we're headed for. And I think we do have to be worried about where our sources of energy are going to come from if we get a cooling plant. We're thinking the wrong way about this, and I think that's where the evidence is pointing to, and I think that's what we should be spending our effort to try to solve in terms of our future energy needs. Planning for cooling rather than warming. That's my presentation, so my advice is to stay warm.
Okay. Running out of microphones here. Okay, everybody can look at their watch and see that we're clearly not going to be out of here at 9. So, my vice president just came to me. We're going to do 5 minutes if you need water or bathroom, and then George Taylor's up in 5 minutes, folks. So, hang tight, and we'll get George going in just a second. be about 3 minutes, folks. 3 minutes to George Taylor. Okay, folks, 1 minute, please. If we can have everybody please take a seat. 15 seconds, we're going to get started. Please take a seat, folks. Okay, folks, if I can get your attention, please. Please try and find a seat real quick, and we'll move on to our final presenter tonight, George Taylor. Everybody can find a spot. Thank you, everybody, for staying longer. One quick note I wanted to make, it was brought to my attention that Chuck Wise's presentation was very technical, and it may have been very technical. There will be a test on it later. It was done that way very specifically because his information is going to be peer-reviewed. So it was important that he also gave that in a way to which these folks are going to review his work, because there's been some question about this being peer-reviewed. So hopefully everybody got that well. And thank you very much, Chuck, by the way. Okay, let's move on to our final presenter this evening, and we'll do Q&A after for those of you who can stay. Okay, folks, George Taylor is our final presenter here tonight. Mr. Taylor is currently the president of Applied Climate Services in Corvallis, Oregon. George received a bachelor's degree in mathematics from the University of California at Santa Barbara, and a master's degree in meteorology from the University of Utah, a very good weather school, by the way. He's been certified by the American Meteorological Society as a certified consulting meteorologist. George has been an active in weather and climate work since 1971. That's 2 years before I was born. I shouldn't have said that. Just kidding, just kidding. I knew it. Yeah, exactly. Okay, from 1989 until 2008, he was employed by Oregon State University. There is no guitar with him tonight. Would we be singing El Nino or La Nina? Because the latest GFS looks like El Nino to me. Okay, so he founded Oregon Climate Services in 1991 and served as a state climatologist for Oregon from the time of his appointment, in 1991 until his retirement in 2008. Ladies and gentlemen, please welcome George Taylor.
Retired has a nice ring to it. I was thinking about this. Two good things about being retired. Number one, you don't have to tuck your shirt in. And number two, you can say what you want to say without any repercussions from anybody. I haven't changed my tune since I retired when it comes to this subject, so I don't know if that means I've been corrupt and I still am, or if I'm agreeing with myself. I don't know. I just wish I'd brought my guitar. This would be a nice time to do the La Nina song. It really would. But I don't have it, so never mind. I'm going to kind of hurry through my stuff because it's real late, and you're probably sick and tired of all this climate stuff. So here we go. Here we go. There we go. You've seen all kinds of stuff like this. This is an old Newsweek cover. All kinds of things have been blamed on global warming, or as they say now, climate change. And I've seen a lot of changes in attitude and also a lot of changes in data. But here's the fundamental question. What causes climate to change? Everyone wants to know. Is it human causes like greenhouse gases, land use change, smoke, dust, aerosols, and stuff? Or is it natural causes like sunlight and ocean and volcanoes and stuff? You know what the answer is? Yes. Some combination of those things causes climate to change. And I don't think anybody really knows exactly what it is. I think we all have opinions on the various magnitudes of these things, but there's a lot of uncertainty. We live and experience a climate system that's amazingly complex. It humbles me to know how much I don't know. And the older I get, the less I understand about climate. So either I'm getting wiser or I'm getting stupider as I get older. I hope it's the first one. But anyway, all else being equal, increasing the amount of greenhouse gas in the atmosphere should increase the temperature. The only questions are about how much and how do we measure it. Now, I'm not a modeler like Chuck. I'm a pretty simple guy. And to me, it's like a good detective story. You get certain clues, and then from those clues, you come to a hypothesis and then maybe conclusions. And so what I'm going to show you are some pieces of evidence that I've collected. I've collected a lot of other pieces of evidence. But these are pieces of evidence which, to me, support a conclusion. And I'll probably already know what my conclusion is, but I'm not going to tell you yet. But I want to divide the world into two different categories and try not to take these two too seriously. But the first we'll call alarmists, and you've heard that word before. And alarmist is not necessarily a bad thing, because if there's a fire and somebody sounds the alarm, that's a very good thing to do. Paul Revere was an alarmist. He spread the alarm to every Middlesex village and farm on the 18th of April in '75. Hardly a man is now alive who remembers that famous day and year, you know? But here's something from one of the chief alarmists. So let me just define an alarmist as someone who believes that humans are largely responsible for climate change. And one of them is Al Gore, who said climate change is occurring far faster than even the worst predictions of the UN's group. And new evidence shows the climate crisis is significantly worse and unfolding more rapidly than even those on the pessimistic side of the IPCC. Now, why Al Gore? He was the vice president. He, a few years ago at a technical meeting in San Francisco, the American Geophysical Union got a standing ovation from the scientists. So there are a lot of people who consider him a hero and a spokesman. Oops, sorry. Here's something else that Al Gore said. I believe it is appropriate to have an over-representation of factual presentations. How dangerous. What does that mean? An over-representation of factual. As a predicate for opening up the audience to listen to what the solutions are. I'm not going to interpret what he said. I think okay. And here's what he said about the other side, the other group, the deniers. The term deniers really came from Helen Goodman, who said that those who deny the reality of human-caused climate change are like those who deny the Holocaust. And I find that to be offensive and troubling. Nevertheless, according to Al Gore, they're in such a tiny, tiny minority, almost like those who believe the moon landing was staged and the world is flat. The world is flat. Looks flat to me. Okay. All right, so something that alarmists say, and this is from the governor's, my buddy the governor. Do you know it was 5 years ago next week that thing happened in OMSI that I was at and Phil Mo was at when the governor got really upset with me. It's 5 years ago. Anyway, scientists are very sure that the Pacific Northwest is warming and that since 1975 the warming is best explained by human-caused change to greenhouse gases. I don't know, it's hard to really determine that, but let's just see what history tells us. The pesky deniers have a tendency to fall back on history. And this is a very typical mean annual temperature trace, or time series as we call it. In this case, it's Bend, Oregon, through 2007, and things have actually cooled since then. But what we see is, throughout Oregon, throughout the U.S., throughout the Northwest, a warm period in the 20s and 30s, a cool period in the 50s, 60s, then a rise in temperatures up through the late 90s, and then the leveling off or a decline after that. And that's a very, very typical pattern that we see all over, except in places like Portland Airport where there's significant land use change and you get a very different pattern. But at rural stations, this is what we tend to get. This is Condon, Oregon, over in central Oregon. Again, big spikes in the 20s, 30s, early 40s, and cooler and then warmer. But the warmest time was back here. What we see in Condon, and in fact in a lot of the dry places, is greater interannual variability, greater year-to-year variation than we see over a long period of time. And my favorite station, Corvallis, because I lived there, 1895 to 2007, looks the same. And the reason I like Corvallis is it's in a rural area and has been for a long, long time. And Oregon State University takes some measurements, is very careful about how they take them. But again, we see the same distribution of a warm here, cool here, and some warming, but a leveling off. If we look at the last 20 years in Corvallis, there's actually a pretty significant decline in temperatures. And that's only through 2010. 2011 was about 3/4 of a degree cooler than average, so it was even lower. So something is going on, and it's not the kind of steady warming that a lot of people predicted. Oregon statewide temperatures, and this is the last 15 years, also show a decline. There was kind of a spike in 2002, but general decline in the last 15 years. So it really doesn't fit the pattern. If we look at the 18 western states and look at the number of temperature extremes, heat waves, and low temperatures, there's a big spike in the 30s. 30s had a lot of heat waves and a lot of cold periods, and the cold periods began to decline, and so did the heat waves, and in recent decades we've had fewer extremes. This is U.S. state maximum minimum records for the whole country, and once again the heat waves predominated in the 20s and 30s, teens, 20s and 30s, and the cool records were mostly in the 60s and 70s, and we're seeing fewer extremes. Why? I don't know. Here's just heat waves. It's just heat waves. Again, big spike in the 20s and 30s. and not much since. A few warm years since then, but not too many. Well, so here's what the deniers conclude, and of course, by now you know, you probably already knew I was a denier. So I might as well confess. So this is what this denier says. In Oregon and the Northwest in the U.S., the warmest decade was in the 30s. What we've seen is a cyclical pattern of ups and downs, and the temperature extremes are becoming less common. Snow. You've already seen one of the snow slides. Gordon showed it. But this was something that the governor said, the governor of Washington, Christine Gregoire, in 2009. We've already lost 20% of our snowpack over the last 30 years. My friend Mark Albright, who used to be the state climatologist in Washington, decided to see if this was true. And about a year and a half ago, he plotted 30 years of data for Washington for all the stations west of the Cascade Crest. And that's what he found. There's an increase. Maybe that's really what she meant. Just a little typo. This is a chart that's similar to something you already saw. And this is based on analysis of snow done by a group from the University of Washington. At that time, the state climatologist was Phil Mote. And they did analysis of snowpack in the western U.S. from 1950 to 1997. Now, they did this in 2005. So there were some years subsequent to 1997 and some prior to 1950. But the point that they made was that about half of the snowpack was gone. And if that trend continued, now think about this. To about there, we have no snow on April 1st. So that would be a bummer. And so, for several reasons. But I won't go into why. So I plotted 1950 to 1997 data and got a 43% loss. I thought, boy, they're right. And then I realized, well, but there's data since 97 and there's some data prior to 1950. Remember Paul Harvey, what he used to say? I decided to see what would happen if I looked at the rest of the story, and this is the rest of the story. There's Roaring River in the Cascades east of Salem. Same chart on top. There's a chart at the bottom showing all the data. And if you look at the data from 1929 to 2009, there's no trend at all. How can that be? Must be just that, no, here's Three Creeks Meadows in the Ochocos. You get about a 35% loss at the top versus, again, no change at all if you use all the data. And this is Annie Springs near Crater Lake, same deal. Now I've updated 3 of these through data through 2011, so here's Roaring River. I don't know, I didn't draw a straight line or any kind of a curve on this because I don't know what to do with it. But I'm not alarmed by it either. It doesn't look like the snow's going away. There's Three Creeks Meadows, kind of the same way, and there's Annie Springs. So my conclusion was, oh, by the way, if you take all of North America, the snow extent in the winter, there's some really snowy years and some that aren't so snowy, but the trend through 2010 was actually slightly upward. How can that be? Northern Hemisphere snow extent, pretty much a straight line if you graph a correlation line on it. So what the deniers concluded was snowpack shows a cyclical behavior rather than a simple decrease, and yeah, okay. Alarmists say CO2 levels are a dominant factor in climate change, and this denier says, what really is responsible is the tropical Pacific plus changes in sunlight. And I think that those are the two smoking guns in this detective story. The tropical Pacific, and it's illustrated here in its 3 basic phases. In the middle is the normal or the average. You see that black line in the middle is the equator. Over on the right is South America and Central America, and over on the left is Indonesia, Northern Australia, and all that. And the line in the middle is the equator. The colors represent the sea surface temperature. So blue is cold, orange and red orange is warm, and yellow is kind of in between. So top is La Nina, middle is normal or average, and bottom is El Nino. So El Nino and La Nina, or the El Nino Southern Oscillation, represent an oscillation of sea surface temperatures and winds and other stuff. But this window that you see right here is called the Pacific Warm Pool. This is the most significant terrestrial source of heat, the most significant source of heat on Earth to the atmosphere. There's more heat that comes out of here than anywhere else. Warm water comes out like crazy. Think about a hot tub outside a motel on a cold winter night, and it's steaming like crazy and losing heat to the atmosphere. Same thing happens here. That warm water loses heat to the atmosphere like crazy. And the El Nino overall, you look at the one on the bottom, there's a lot more yellow and orange than there is at the top. There's a lot more blue at the top of La Nina. So generally an El Nino tends to release more heat because the water is warmer at the surface. And the La Nina tends to release less heat. And what El Nino does is it causes global warming. What La Nina does is it causes global cooling. Now this is on short periods of time. And over the course of time, these happen in cycles. And we call this cycle the PDO, or the Pacific Decadal Oscillation. Generally speaking, the periods that are shown in red tend to coincide with El Nino events. So 1920 to 1945 or so, a period of more El Ninos, positive PDO, and this is a period with all the heat waves and warmer temperatures. It was cooler in the 50s, 60s, and early 70s in the blue. Negative values of PDO, more La Ninas, fewer El Ninos, more snow, colder temperatures. And then back in the mid-70s to mostly reds until the late 90s, and then since then it's kind of jumped up and down. But there's been more blue than red since in the last 12 to 15 years. So here's the evidence that El Nino and La Nina cause significant changes in temperature. The black represents the El Nino and La Nina value, the Nino number. And the positive values up here are El Nino events, like that really big one in 1998, 97, 98. And these represent La Nina, so it oscillates back and forth. And then the red represents the lower troposphere temperature, the temperature well above the surface, measured by satellites. And notice how well these correlate. That when the black one goes up, the red one goes up, and when the black one goes down, the red one goes down. But if you notice also that the black one always leads the red one. So here, for example, the black goes up, and then the red follows, and then the black goes down, and the red follows. And the same is true really throughout the chart. Now, when you see one thing that follows another, that tends to mean that the one that is leading is the cause. I'm a simple guy. That's what I conclude from this. Except that there are two exceptions here. And one of them is right here, where there was an El Nino event, but the temperatures only went to there. And there was one here where there was an El Nino and the temperatures went down. Now, how could that be? Well, this was a volcano called El Chichon, and this is a volcano called Mount Pinatubo. Tropical volcanoes that emit a lot of dust tend to cool the atmosphere. And that's what happened. The temperature would have been a lot higher here if there hadn't been a volcano. It would have been probably up into here. So if you take volcanoes and El Nino, La Nina, it explains pretty much all of the variation in temperature since 1978 when they began the measurements. Therefore, in my conclusion, the tropical Pacific, and in this case throw in a few volcanoes, really is the culprit when it comes to climate change. Sea level rise. Okay, I'm going to hurry through this. What does history tell us? Well, over the last 20,000 years, sea level has gone up a lot. Oregon has actually shrunk in the last 20,000 years because the sea level has gone up about 400 feet. But that's because we're in an ice age. But if you take just this little bit of what looks like a flat curve, this is a scale of tens of meters, but go to this scale, look at the last 8,000 years, and things seem to be leveling off over the last couple thousand, at least at the scale of meters. And then if you zoom in on the last 100 years, here's what you get. Sea level has been rising over the last 100 years at a rate of about 6 inches in the last 100 years. This is from tidal gauge records in the black, and the red is from satellites. And there is some evidence that this rise rate is slowing down, but the Earth continues to recover from the last ice age. And because of thermal expansion, the oceans are still slowly rising. And I think this is going to continue. If I had to predict this, I will predict it. I'm going to predict that sea level will continue to rise over the next, for this century, and another 5 inches. There's my prediction. 5 inches more. Now, if you own some vacation property on the Oregon coast and you're really close to sea level, now would be a good time to sell it, because if 5 inches bothers you, or even a foot bothers you, now is a good time to sell. But Al Gore said 20 feet, and I tend to disagree with that. I think sea level is going to rise, but this was an interesting one that was already shown. I don't remember if Gordon showed it or Chuck showed it, but this shows a steady rise, although in the last few years you can see that the rise has become less significant. There are a lot of values that are down in here. So I don't know, but I think sea level is still going to rise. Hurricanes are increasing in intensity. If we look at the data, this is from Ryan Maui of Florida State. Tropical cyclone accumulated convective energy. It's basically all the energy from all the tropical cyclones. Doesn't look like it's increasing to me. I don't know. But I'm a simple guy. The Arctic. The Arctic is melting. This is from Igor Polyakov's 2003 article, and sure enough, from 1970 to 2000, this is Arctic surface air temperature. The Arctic temperature grows. There's a lot of blank on that, though, because I'm going to show you the rest of the story. Here's the rest of the story. The warmest decade was the 1930s, the warmest year was 1937, and that's still true, even though his data only went to the year 2000. And one interesting match is if you couple the PDO with the graph at the top, it seems to match pretty well. At least to me it does. I'm just going to skip Antarctica. The ice around Antarctica is growing, and I'll just tell you that. Last thing I want to talk about are glaciers. People talk about glaciers and how they're melting, and they are. Here are two pictures, 1910 and 1997 from Glacier Park, from the Grinnell Glacier. And notice in 1910 there was a lot bigger glacier than there was in 1997, and this is not the same now. So without a doubt, the glaciers in Glacier Park have melted. The way that these are usually categorized or quantified is the height of the terminus, or the bottom of the glacier. So in 1910 it was here. In 1997 it was way up here. So it grows from here up to here. And that's a pretty good yardstick. So yes, glaciers have melted since 1910. There was an article in a journal article in Geophysical Research Letters. The main author was Gregory Peterson, and he looked at these, and they studied glacial moraines and dated them. And this is what they came up with for one of the big glaciers of the height of the terminus. And here's 1840 when their study began, or the data began, up through, 2020, which is in the future. And what they concluded was, beginning around 1840, there was very little glacier dieback, and then things really started to get going in 1920 or so. And in a 10-year span, most of the melt occurred. Now, most of the CO2 enhancement started in World War II, which is out in here. So whatever caused this was definitely not CO2 changes, but something else. And they concluded it was because that was a very warm, very dry decade throughout the Glacier Park and the U.S. for that matter. And since 1930, there's been a little bit of melt, but not very much. They also took glacial moraines back to 1700, and what they concluded was that the beginning of the photographic record, which is the middle part of the 19th century, coincided with the greatest ice extent at the end of the Little Ice Age. This was a period of about 500 years that ended sometime in the 19th century. And they concluded that the first Caucasians who saw Glacier Park saw it with the glaciers at their very largest, and the first photographs showing the same thing, including this period here of great glacial advance. What they show here is the blue represents periods of advance, and the red represents period of dieback or ablation. And notice in the 20s and 30s this period with tremendous ablation or dieback of glaciers, and since then it's kind of bounced around and not much has changed. So what this does is it puts glacial melt in Glacier Park into perspective, in a historical perspective, and says that most of it happened before the CO2 enhancement and seemed to be due to the fact that it was very dry and very warm. Okay, so now I'm at the bottom line. And then we'll have time for questions. I believe human activities do affect climate in a variety of ways, including greenhouse gases. I think the greenhouse gas influence is very small. Frankly, I think the biggest human contribution to climate change is land use change. When you change land from rural to urban, from forest to agriculture, from agriculture back to forest, you cause very, very significant changes in radiation and absorption and moisture and other things. And one place we can see that is on the US-Mexican border, where land use policies are very, very different. And the temperatures are very, very different, just in the span of a few tens of miles. So I think there is a multiplicity of human effects on climate. Air pollution is one that affect climate. Somehow carbon dioxide gets to be the bad boy, and I think it's not a very appropriate moniker for CO2. I really think the effect of CO2 is pretty minimal, but I think the human effect can be very significant. I believe that natural variations affect climate, and that they have been more significant influences on climate because they do a much better job of explaining observed variations. And I think the two things I mentioned, the tropical Pacific and solar radiation, are the two primary dominant factors. I believe, therefore, the effects of future changes in CO2 are likely to be modest and manageable. And I don't think we can control climate. I really don't. But I will admit, and I'm sure that you'll all agree, because weather and climate guys are wrong so much of the time, many aspects of climate remain poorly understood. And that's all I have to say.
Okay, I'm going to take a quick poll again. Raise your hand if you got questions for any of these three gentlemen here tonight. Oh, I like that. Only 3 people? Okay. Bobby Corser here, our Vice President. And by the way, I'd like to make one more plug for the Oregon chapter of the AMS. If you're interested in joining, it's $7 a year. Please see John Renier, our treasurer, at the back. If you enjoyed this presentation tonight, drop a buck in the hat back there as well. If you have a question, please come up here to Bobby Corser here with the wireless mic. And George, if you could join Gordon and Chuck over here. It sounds like we're only going to have a few Q&As. And for those who are leaving, thank you for coming this evening.
So just some basic ground rules. Can we get your name, please? And if you have any affiliation with the group or anything like that. One question. And
could I have everyone's attention, please? We still have a meeting Q&A going on, so if you're exiting, please try and exit quietly. Appreciate that. Do these guys have a mic? You got the wireless over there, guys? Oh, here it is. You gotta come get it, though, because I'm wired. As Bobby was saying, go ahead, Bobby.
Just one question, and if they have a chance to ask a question back, we will let the person asking the original question get the answer first time.
Lisa Michaels, Chairman of the Conservative Party, Oregon. And I want to ask you, George, when you said that there were the 2 main factors that affected the change in temperature was the sun and the Pacific Ocean, but you didn't mention the Atlantic Ocean. What extent does the Atlantic Ocean mirror what happens in the Pacific Ocean?
Is this on? Yes, it is. The tropical Atlantic is a lot smaller than the tropical Pacific. There's certainly an effect that the Atlantic has on global climate, but I believe that the tropical Pacific has a much bigger effect just because it's so much larger. It's like the tropical Pacific is a swimming pool and the tropical Atlantic is a wading pool almost. It's not quite as extreme as that, but it's a matter of degree. And I think my top of the head number would be that there's probably 3 times as much effect of the Pacific than there is of the Atlantic.
My name is Alan Rogers, for Dr. Fulks. If doubling the level of CO2 would, all else being equal, raise the global temperature, the opinions vary from 0.2 degrees to a half a degree, but doubling the level of CO2 would increase plant growth, food production by a very significant amount. Why don't we ever hear anything about that?
Well, I think is it on? Okay, I think we do. We already have a population on this planet of about 7 billion people, and our ability to feed them has actually improved over the years, not only from the work of Norman Borlaug and other agronomists, but from the additional carbon dioxide transfer. So we're already better off. It seems to me that it's foolish to try and reverse things. We know that if you enjoy tomatoes in the winter, you get them from greenhouses where the CO2 has been enhanced up to 1,000 or 1,500 parts per million by volume. Carbon dioxide is a benefit to plants. If it is a problem in terms of a little bit of additional warmth, that really is a benefit, though, in the end to the plants. So it's hard to see that by any scenario it would be a problem.
Yeah, Chuck, question for you. Appreciate from all three of you the technical competence and integrity. If you were to know of a climatologist who really adhered to severe climate change, and he published for public consumption information for the public, like this public here, and I'm highly confident in science, information from which he had subtracted, taken from a technical journal, a sentence, and to show his point, cut the sentence off and then put a period where it didn't belong. Would you expect that scientist to admit that, come forward with it, claim it was a technical error or a typo or an editorial error? How would you expect him to read it?
Well, I think that's what the peer review process is about. When somebody publishes something, an idea, a hypothesis, anything in terms of a paper, their peers who are the same arena that they do are supposed to look at that and catch those kind of errors. The authors certainly should. And, oh yes, if there's an error, by all means, you should admit this. Absolutely.
Like the test of the Dr. Fulks, and you know that's not entirely hypothetical, Dr. Fulks.
Like the what?
It's not entirely hypothetical. My question.
I'm not sure.
I think you're probably referring to my op-eds in the Oregonian where I'm word limited, and what I try and do if I quote someone is catch the essence of it. I obviously cannot include an entire quote. One always does a better job with more material, but even tonight we're limited by 30 minutes, so we certainly don't get it all.
And we cut the sentence off mid-sentence, put a period there as though you were quoting the whole period. That was okay.
I don't know specifically what you're referring to. If you tell me, I'm happy to respond to it.
Okay. I think you and I both know what it was.
Okay, next question. And for the record, sir, can we get your name? I don't think we got your name at the beginning. I'm sorry, what was the name? Dick McQueen. Okay, thank you, Dick. I appreciate it. Next question.
I guess this one is maybe for George.
And your name, sir?
Bert Bissell. And given the heat island effect and the increased temperatures in urbanizing areas, what kind of policy, this is just for my information, maybe for everyone else here, what policy does the Climate Research Unit and the Goddard people and the NCAR people use? Do they average the urban stations and the rural stations represent the total land area, or how is the game rate going to fit in your view, or is it going to be a fair average representing the entire landmass area?
Well, Vern, the whole process of correcting temperatures is a mystery to me, and I don't know how they do it. And quite frankly, the idea of coming up with a single temperature for the surface of the Earth seems like an impossible task. And it's one that I think, I tend to look at local effects individually rather than coming up with a single composite number. It'd be like, what's the average temperature in this room? Well, you could measure it in a lot of different thermometers in different places. Well, what if it's on my tongue? Or against the window? Or, I mean, there are places where you get that kind of interference in temperatures. I think a single global temperature really doesn't make any sense. And I don't know how they get there.
Next question.
Hi, I'm David Morse. I'm old enough to remember back in the 70s when everybody was worried about an upcoming ice age. And all that stuff. What happened to all that research and all that data? It seems like all of a sudden that disappeared and we're going to be burning up.
Well, yeah, some interesting material sent to me the other day by Roger Cohen, who's a fellow of the American Physical Society, and he was pointing to an article out of Time magazine back around 1971, I believe, that lamented the fact that the climate was cooling and that the armadillos were moving south as a consequence of moving to a warmer climate. There's a recent article, somewhat breathless, somewhat hysterical, about a Scientific American that has the armadillos marching back north. So armadillos are probably only second to man in terms of being confused about climate change.
Next question.
My name is Tom Mahelich, and I'm not affiliated with anyone. This is for George. You mentioned at the end of your talk that the next ice age is due to arise 1,000 years from now. You base it on the Milankovitch theory, and how much of that, how do you calculate that? I mean, the orbit right now is spherical. Do you base that on the precessions of seasons, or what? And I've seen 3 different numbers in the last month. One was year, I saw a 1,500-year figure and also a 3,000-year figure. So I was just wondering what you base it on.
Well, I think what you first want to do is look at the entire record we have of Milankovitch cycles. And those have a width of these warm periods being about 10,000 years. So simply on that basis, we are headed for another ice age. How close are we to it? We are into the Milankovitch cycle such that the Earth's closest approach to the sun is now in January. It used to be in July. Having done that over a 10,000 year period, we're in the coldest arrangement. If you look at the global temperature at this point, when does it peak? It peaks in the northern hemisphere summer, yet we get about 88 watts per square meter, an enormous amount more energy because we are slightly closer to the sun this time of year. In fact, the perihelion was, I think, around January 5. So that is an ice age configuration. The much greater landmass in the northern hemisphere with much less heat capacity allows us to warm up when the sun is in fact the weakest. What triggers the ice age is unclear. It's presumably a massive snow cover, perhaps something related to volcanoes, or something related to the year without a summer, which Thomas Jefferson noted about 1815, 1816, which then led to the greatest famine in the 19th century. Freezing temperatures in New England, loss of crops and whatever. But once you get something like that, once the ice age gets a grip on you, the albedo of the planet has changed. It has gone to much whiter and much more reflectivity of the energy coming in, so the effect of the sunlight is lower and you drop into an ice age. But don't be too concerned about that, because if you notice from the ice core record, there's quite it takes quite a time for the oceans to respond in the carbon dioxide signal that they put out, indicating that they hold up in temperature much longer than you might think otherwise from the solar component or the orbital component dropping away. So the oceans are a very good buffer, and they prevent us from going into an ice age even if other conditions are right, for something of the order of 1,000 years. So 1,000 years or more would probably be a good guess, less than 3,000 years, because none of these interglacials have gone beyond about 13,000 years.
My name's Steve Shaw. First of all, earlier when you said that 1,500 feet will never be climbed again, volcanologists will say it can be rebuilt and then we can all climb it. 98%.
That was Gordon that said that.
That was later.
I said it, but it was Gordon's quote.
Right. I think there's maybe more alarmists left at Oregon State than there are deniers, and probably by a big margin. But I've read a lot about the circumstances coming out of there, and in the last couple of years there's been establishment of 5 marine reserves off the coast of Oregon. The main genesis behind that, and all the publications and advocacy was always led by the notion of global warming caused dead zones and global warming caused ocean acidification. Are either of those true? Does Oregon State have any science? And why did we need the marine reserves?
I think you should also ask why Jane Lubchenco is now in Washington rather than at Oregon State University.
Chuck, do you or George have any thoughts on that?
Well, I don't want to get too much into the politics because we agreed tonight that we're not going to do that. But
you went to Oregon State, so we figured.
Well,
and George worked there.
They really did teach good science back in the 70s. No, they still do, but it's unfortunate that a lot of this stuff gets politicized like it does. And I don't think there's any evidence that all the dead zones are part of climate change as advertised by them, because if you go back in the historical record, you read newspaper articles, there were times when a bunch of dead sea life washed ashore, and there were reports of this on the Oregon coast. They may have discovered more of it, but with their measuring instruments now that they've got them in place and they're looking at all these things, but I don't think the problem is new. There's no evidence that it's new, and I think it was caused a lot by the Pacific Decadal Oscillation and La Niñas. The cold water upwelling, I think, creates these dead zones, and they oscillate back and forth. I don't think George would disagree with me on that.
You're ready.
There's a process, it's called upwelling, that brings deep, low oxygen water to the surface, and along with it a lot of nutrients, and that is vital to the health of the fishing industry. We used to have celebrations when the spring transition would begin, when the north winds would blow and the upwelling would begin, because it meant generally we were going to have a good year for fish and other marine animals. And suddenly it seems that upwelling is the bad guy, and I don't get it. So, but I'm just a simple guy. I don't know.
Gentlemen, first of all, I'd like to thank you. I'm Doug Devine, and I'm here as a private citizen, an interested citizen. I'd like to thank you for your great, excellent presentations. I know I didn't understand all of it, but I think I got the gist. My question, if you were to select, and this is any or all of them, if you were to select one substance in the climate that could be attached a dollar value to and to be controlled by that dollar value, what would it be? Or is that off limits?
Yeah, I think one thing you have to realize is that the dreams of controlling the climate have been around for a long while. I talked decades ago with Jim Little about whether there was any reality to enhancing rainfall in the Santa Barbara area by dumping silver compounds there. And apparently that was one area where they actually could show a slight enhancement of the rainfall by the climate modifications. But other than that, I think there are no indications of humans in this country, at least, being able to modify the climate. I know the Russians, for many years, were involved in all sorts of experiments to try and control their harsh climate, and they were all failures. Maybe somebody else did.
Well, there have been several what we call geoengineering proposals that are massive engineering things that are designed to change things like climate. Edward Teller said we could control global warming by exploding nuclear weapons in the atmosphere that would create lots of dust and block out sun, but you know, for every elegant solution like that, you often have some unintended consequences.
One thing I can add to this about this man controlling the climate thing is I'm really taken back and kind of I just don't understand a lot of the things that I read from the Oregon Global Warming Commission, this carbon reduction strategy. They put this thing into place, our local governments, and I can't follow the logic of it because they claim if we reduce our emissions we can bring the temperature down. But I wrote to Phil Mote, I wrote to Mark, your boss, former boss there, Mark Abbott, and they never answered me directly to my question. And I said, you know, if you do a simple off-the-cuff calculation about reducing carbon emissions, Oregon emits, according to their data, 68 million metric tons of CO2 per year. And if you do a simple off-the-cuff calculation, you could wipe out that entire 68 million metric tons of CO2, and you're not going to budge the free CO2 air concentration in the atmosphere, which is what they plug into the climate modeling to get these really ridiculously high temperature forecasts. So if it was really controlling the climate, what kind of bang are we going to get for our buck if we do that? I mean, there's none that I can see. You could wipe out the 7 billion metric tons for the whole United States and you'll only move it downward 0.72 parts per million by volume. That's a rough estimate. But it's going up over twice that rate right now, and the reason is there's a lot of emission coming out of the ocean. We can do nothing about that. So the reduction strategies are silly. They don't make any sense, even if the carbon was controlling like they claim it was, which I don't believe, and the evidence doesn't show. What are you going to get if you try to reduce it? You're wasting a lot of time, you're going to create a lot of suffering, and you're going to get nothing for your attempt to do that.
2 questions left. 3 questions.
My name is Andreas Schmittner. I'm a professor at College of Earth, Ocean, and Atmospheric Sciences in Corvallis at Oregon State University.
Good.
I've been working on climate since about 1999, when I did my PhD in Switzerland, and moved here about 5 or 6 years ago. I've published about 40 papers on climate change, and I've been to many conferences. What I can see in those conferences is that most scientists who are actively working in the field, who are publishing peer-reviewed papers about climate change, have very different opinions and very different views than what I've heard tonight. In fact, many are sincerely concerned about the effects of CO2 on climate, and it is known that CO2 does warm climate, contrary to what has been said tonight. I want to give you a quick example from my own work. I'm very much interested in paleoclimate, which means past climate changes, and there were some references to paleoclimate today. But at the height of the last ice age, about 20,000 years ago, there were huge ice sheets on Greenland and in Northern Europe. The sea level was 120 meters lower than today. So climate in general was much colder. We have an idea about how much colder on global average. It was about 3 to 4 degrees colder than today, global average surface air temperatures above the ground, that is. We know this from reconstructions. But CO2 levels at that time were also much lower than pre-industrial. So they were 180 parts per million compared to 280 parts per million before the Industrial Revolution, before any effects of mankind. So the climate at the last glacial maximum was much colder, and it had lower CO2, and that lower CO2 at that time had something to do. It is part of the reason that the last glacial maximum was so cold. If you do not consider that, you do not get a cold last glacial maximum. So CO2 is a very important driver in past climate changes. We know that all paleoceanographers, all paleoclimatologists know that, and denying this is
in the essence of time, since we have to vacate this building here at 10 p.m., let's get to the question for the panel, if you could, because we still have 4 people behind it.
Well, I guess it's more of a comment, but I think everybody can, all of the speakers can comment on the fact that paleoclimate data show that there's a tight link between CO2 and climate.
There is some warming by it, but did you see the radiation graph that I presented tonight? Do you agree with me, sir, that if you looked at that, the absorption coefficients at 15 microns are so strong, you get almost immediate absorption around the 15 micron band, very close to the ground, even at the concentrations that you're talking about. And so you get a big bang for the buck. I agree with you. You get some enhancement of the climate by putting the gas in there initially, but then when you try to grow it from that point on out, and there we're talking about the wing absorption and emission, you know that the coefficients drop way off, and you've got to go through a much larger concentration of atmosphere to get a result, which means you're not going to get as much energy on it. So you did get a big bang for the buck, but it occurred at concentrations much lower than we have now. The additional CO2 added is going to only try to change things very slowly, and the founding work shows that water vapor is self-constrained by its own radiative absorption and emission, and adding CO2 is going to enhance the hydrological cycle by doing that, and you'll get some enhancement in the tropics of warming by where the real strong absorption is. But I'd like to know where the evidence is that the current concentrations going up are really contributing much of anything. That was the crux of what I was showing tonight.
I don't agree with that, and I do think that the paleoclimate data show that there is a strong effect of CO2.
Okay,
Well,
Chuck.
George Taylor wants to say something to you too, sir.
Yeah, and George and Chuck and everybody, and I do respect your questions, by the way, and your people. We've got to move on. We have to vacate the room by 10.
Really quickly, Andreas, don't go away. You and I were colleagues for a while. We kind of agreed to disagree, and you were one who showed me a great deal of respect for a long time, and I thank you. And yes, there is a difference of opinion on this subject. Different people have different ideas, and I might be wrong, and you might be wrong, but you showed me just through your example of how to disagree with someone and still respect them. So thank you.
Thank you. Next
Let me
question.
get back to the science for just a second here. I think one thing that's important to point out with the data from the ice cores on temperature, which is a very good proxy, and carbon dioxide, which is a poor proxy, we still know that there is a substantial lag, despite what Al Gore shows that this sort of behavior and then the carbon dioxide doing the same thing. There is, in fact, a lag of about 800 years, which says that one is the driver and one is the responder, and that is hugely important to understand. It says that as the oceans warm up, the carbon dioxide comes out, or as they cool down, the carbon dioxide is absorbed. So that is hugely important. Well, the other thing I might mention too, going back on paleoclimate data, well, far beyond the spatial periods that we have records for, we see no correspondence between carbon dioxide levels that have been estimated and the temperatures that have been estimated for those periods. So it just simply doesn't work.
I think you guys are going to agree to disagree on that subject. So, and I hope you guys can carry that on a sidebar conversation. Robert.
Rob Woodard, I'm a dues-paying member of the Oregon chapter of the American Meteorological Society. $7 a year. Last few years, $35 in the pot for me. And I've often thought it would be interesting if your cold predictions come through when they start requiring us to put more carbon into the atmosphere. My question is, the theory that you have, and I generally agree with you, is that humans aren't causing any appreciable part of the climate change that we see. Theories can be useful, need to be defeatable. In other words, there has to be something that would appear that could convince you that you were wrong. And since we saw here that about 90% of us in the room during the presentation tonight generally agree with you, and you guys live this science a lot more than many of us here, what would you need to see from people who support human-generated climate change to start convincing you that your opinion here is incorrect? What sort of data, what sort of time period, what sort of evidence, so that we have an idea of where that fight might appear. Whether or not you think it'll appear, just what do you think it will look like?
With me, the really killing thing to me on this idea that CO2 is a climate driver is just matching up the time periods, the actual change in temperature, and then compute the changes in radiative forcing off of CO2 and water, and the actual temperature, which all vary the optical depth. If the modeling started showing that the water vapor column went up like they said, we saw a tropical hotspot develop, if the main signatures or fingerprints of anthropogenic global warming showed up on those models and the real measurements, I would then reverse course. I really don't care about the politics as much as I do getting the science right, because with the science, that's where, if the science is correct, that's where we're going to get the good public policy. So I would change course if we could see that, but right now there's no evidence of it. If you actually run the numbers, I can only account for 8% of the temperature change, and that's not considering evaporation or any changes in cloud cover, which we know these things have an effect on, but we don't have a way of calculating it. So that's where I'm coming from.
There has to be a real signature that's attributable only to carbon dioxide. None of this nonsense that we continuously see of I can calculate all of this, the sun has such and such effect, carbon dioxide has such and such effect, and we wouldn't get the present temperature if we didn't have carbon dioxide. That's nonsense, because a lot of the effects are not that well known. So there has to be a real identifiable signature. For instance, on a cold winter night in the Arctic, the temperature doesn't any longer plummet down to the dew point to where you have cloud cover and whatever stops further plummeting. But we still see it simply plummeting to the dew point. And we've seen that remarkably at Fairbanks this year.
Thank you, Robert. 2 questions left.
Thank you, gentlemen. My name is Vaughn Longenecker. I'm a simple man. And I would, and I would like to know if there's some relatively simple literature, book, materials that not only for my benefit, but also when I go out to discuss this with others, if you could recommend something.
One author I would recommend is Pat Michaels, who is former state climatologist for Virginia, and who writes amazingly well and in a pretty straightforward, simple manner that's understandable even for simple people like us. He's written a lot of books. Patrick Michaels.
Oh, I disagree. Bob Carter out of Australia would be the one I would read. If you write to me at my email address, I'll send you a paper that he put together. He's also written a book. He is excellent. He's a geologist.
I really like Anthony Watts' website. I don't know if any of you out there have heard of it. It's called What's Up With That, not WH, but WATTS. What'sUpWithThat.com. WUWT for short. He's a meteorologist like I am, but he doesn't really give much of his own opinions on climate, but his website is widely read because he has some really respectable scientists from all over the world that have published on the site and offered opinions on this stuff. And they put out some really interesting articles. They're really meant for the lay people, and they're very easy to understand. I really highly recommend them.
We're going to give the gentleman with the OSU hat right there the last say. So just 2 left. Thank you.
First of all, I want to thank you guys for doing this tonight. This has been really educational, and I really appreciate you guys taking the risk to do this. In your professional opinion, where do you see the trends going as far as popular acceptance of the denier theories, which I very much support, but I was wondering how do you perceive the trends? Or is it becoming that deniers are becoming more ostracized, or do you think there's becoming a wider acceptance among the scientific community that they're rethinking their data and that this might turn around in some future, hopefully close time period?
I think the people who really are sold on the idea at the academic institutions are digging in. I don't see any indication that's going to change. I think that's actually getting worse, just evidenced by what happened here over the course of the last year. But I actually do think that because there are scientists, particularly those that are emeritus faculty from a lot of these universities, are now jumping into the arena and publishing things and putting things out that are read by the public that are very convincing that these very tightly held theories in the academic institutions that are making a lot of money with the research grants are wrong. So I think public opinion is swinging in favor of what we're saying, but I don't see a lot of change in the close academic circles yet. I'm hoping that they will come around, but there's different motivations for what they do, that's for sure.
If the climate continues to cool the way it has been, it'll certainly cool the water. That makes our job easy, but of course there are great variations. I'd also simply mention one quote from H.L. Mencken: "A man cannot be expected to understand something if his income depends on his not understanding it."
Final question of the night, sir.
Thank you. This is for Jordan. Vince Wetherill, Sunset Solar Electric, LLC. I'm the owner, man.
Well, I just had a question. My question is, the ocean is a major CO2 sink, and is there any correlation in the data between the rise in acidity levels of the ocean and change in climate, which you have shown on the graphs? For example, does La Nina and El Nino fluctuate with ocean acidity?
Well, the whole concept of ocean acidity is a bit of a misnomer because the ocean is not acid. It's actually on the alkaline side, and there have been some measurements that suggest it's becoming a little bit less alkaline. But number one, it's tough to really reconcile the data because they don't go back very far. And as far as therefore the effects of that, it's one of those data sets that I don't trust. And I'm not sure what else to say about it. Do you guys want to say anything about it?
Ocean acidity can vary quite a bit. For instance, at the mouth of the Amazon, the ocean is probably a little bit acidic because the fresh water is lighter than the salt water. As it flows out over the ocean, it will remain there for a while. And fresh water is a little bit acidic. That's why we have caves, for instance. Mammoth Cave in Kentucky and Carlsbad Caverns are all due to fresh water being slightly acidic and dissolving the limestone underneath. But once the carbon dioxide is dissolved in the water, ocean water is very heavily buffered, and that's why the pH remains basic at around 8 and hasn't changed much, and is not expected to change much because there is a vast buffering agent there that can take care of all the carbon dioxide.
There was one off-the-cuff calculation. I didn't make it. A scientist that I communicate with on some of the websites that I go back and forth on, and some of the scientific circles did an off-the-cuff number. And he's a chemist, Jack Barrett from the Imperial College of London, PhD chemist, and he just made an off-the-cuff calculation that if you took all the carbon in the land masses and dissolved it in the ocean, you still couldn't get a acidic level below 7.0. It would fall, according to him, something like from the 8.1 or 2 value where it is now to around 7.1 or 2. So it's impossible to get an acidic ocean the way the Earth and the seawater buffers all this stuff. That was his point. So it is a misnomer to say as you add more CO2, you're acidifying the ocean. You're not acidifying it. It never gets to that value. It just loses a bit of alkalinity, and then some of these guys say, well, that's acidifying. It's not acidifying. It's not the way it works.
And that's where we have to cut it off, gentlemen. I'd like to thank everybody for coming tonight. Thank you. 2 last notices. We have about 10 minutes and they'll start breaking down the room. Some folks are going back to the lounge afterwards. Please see John Renier if you'd like to sign up or renew your dues for the EMS. Thank you, folks. Good night.